Discussion about vehicular ad hoc networks. I hope most of you would be aware about ad hoc networks at all. So we'll just have an introductory thing about the VANETs, which is vehicular ad hoc networks. Now, when we talk about ad hoc networks, that means we don't have any infrastructure. Basically, the access points only do we have, and we can connect the systems or the nodes, we say specifically, with the help of the wireless connectivity. So similarly, in the ad hoc networks, when we talk of the vehicular ad hoc networks, it is basically the ad hoc networks in which nodes are vehicles. Now, vehicles are the vehicles only that we are taking on the road. They are moving on the road. Now, you can visualize the scenario when we are having some vehicles that are nodes that are moving on the road. How will they connect? I mean, we can talk of the connectivity with the Wi-Fi when we are still, or when few systems are there and they are stable, they are stationary basically, and they can connect. We can very well define, okay, it can be connected through access point. But now we have to imagine a scenario where the nodes are moving. You must have seen the mobile, mobile phones that we carry. Now, Wi-Fi connectivity we don't get on the roads. We only have a data packs that we never we have to connect. But when we are talking of vehicles, which it can face, what problem it can face, that is the main issue. So that was overall, the imagination how the vehicles will be communicating when they are moving. But this has happened actually. We are actually, having vehicles which are communicating with each other. The trial is already being run with the different companies and all. So I'll give you how it works, these standards that we are having for VANET, and how we can simulate it when we have to, do some research into the vehicular ad hoc networks. So first major point is it is an intelligent transportation system. Now, why do we call it as an intelligent? Intelligent means they should be able to convey something each other. They should be able to get the information, retrieve the information, and send back the information to the other vehicle. Now, only issue here is we are using it for a special purpose. Now, purpose of VANET is for a safety, for a human safety, and maybe to little bit extent we can say a commercial applications also, where we want them to use as a internet connective source. So intelligent transportation system basically is the vehicles are conveying to the other vehicle about the scenario of the road. If suddenly a vehicle applies a brake, what happens? The vehicle at the back doesn't get any information as such, but it has to visualize it, just see it, what is happening. Okay? And come to a scenario when the Google, must have thought of the driverless cars. How it is going to check whether the brake has been applied or not. Okay? One way is we can have sensors. Another way is we can have all the GPS systems and all the sensors on the wheels, and everything can be put. But the only issue is when we are adding so much of equipment, the cost increases. Now, who's going to bear the cost? Cost is to be borne by the people who are paying for the cost of the car. But what if we can get a solution which is cost effective? So now what we do, we treat this vehicle as a computer system, you can say, with a network interface card. And another vehicle is having another NIC card. So both of them can connect to each other. Okay? Both of them can connect to each other, and then obviously they can talk to each other, convey the messages. So brake is applied. Okay? The vehicle at the back, which is at a distance of maybe a meter or 2 meters, will get a information displayed on the screen, probably brakes applied, stop. So immediately, if it is a driver taking action, then driver can apply the brake. If it is intelligent vehicle, definitely, or driverless vehicle, it will get the message and further it will be controlled. So this is an intelligent transportation system. Now, those who are aware of mobile ad hoc networks, MANETs, we call it as there is, we can say, there is a 10% of a similarity if we come to actual scenario of a VANETs. There is a 10% similarity with VANETs. Now, why 10% similarity? Both are ad hoc networks, but the challenges that we face in VANET is much more peculiar and complex that we face in mobile ad hoc networks, because there we are not considering any speed. Topology remains almost same. We simply have to connect it. If the nodes are moving at a speed of maybe say 1 kilometer per hour, because we are carrying the mobile phones and we are near around the modems or the access points, and we are simply carrying it. So there is not an issue. But when we are carrying something, some unit or device on a vehicle which is moving at a high speed, then everything changes. Protocols are different, topology changes because it becomes very much dynamic. So scenario is totally different. There are two types of network connections that we come across in a VANETs. It is vehicle to vehicle connection and vehicle to infrastructure connection. Now, what do you mean by vehicle to vehicle? We can have a scenario where we have a totally ad hoc network where we have one vehicle and another vehicle moving at the back or in front or sideways. Okay, they can connect with each other. Another can be when we know the vehicles are sparse, maybe in the midnight when the vehicles are just two vehicles on a road of 1 kilometer or so, connectivity may be a problem because we don't have devices to connect. So that time we require the infrastructure, network infrastructure. So how do they connect? How do they connect? We can put some units on the roadside, and then vehicle can connect to those roadside units, and further the roadside unit will connect to further vehicle. This is how it works. Okay. So two types of a scenario, that is depending upon our choice what we want to utilize. Okay. So we can have either V2V communications or V2I communications. We have a IEEE standard. IEEE 802.11 specifically deals with the Wi-Fi connectivity. 802.11p is specific a wave standard, which is wireless access for vehicular environment. So there are certain protocols defined for that in this standard that caters to the need of the VANETs. Now come across this VANET scenario, how on road it looks like. So each triangle represents a vehicle basically, which is moving on the road. Now we have a road which has got two lanes and there are certain traffic lights on the road. Okay. So vehicles are moving. If you see on the top, packets are flowing among vehicles because we are considering now each vehicle as a device, okay, communicating device. So packets are being flown, information is being flown from one particular vehicle to another particular vehicle. Now the same message can be communicated back by another vehicle as well. On the traffic lights, what will be the scenario? If we consider a traffic light scenario, there would be number of vehicles that would be halted at a particular traffic light. How it is going to work now? Like we say, there is a congestion. If you have number of nodes connected to a single access point, what will happen? Either you won't be able to connect because there would be a lot of packet drop and all. If you have a access point in the vicinity and around 100 people are trying to connect to that access point at one time, so there are chances, there are probabilities high that all of them will not be able to connect because all are contended for the particular connection. So now the issue would be on a traffic light, what will be the scenario? Either there would be a packet drop or because of congestion, quality will not be good. Now to handle these issues, we have specifically discussed the traffic light scenarios as such. What happens in a traffic light? Number of vehicles are standing one after the other, and one vehicle moves, information is not passed to the another vehicle. There may be some obstruction just next to the traffic light. Then what will happen? Okay. information will not be passed because network connectivity is very poor. There's a congestion. So we have to take care of all these scenarios. Okay? Once we are totally relying on to the intelligent transportation system and we are not getting the information back from the system what is expected actually, so it can create a chaos. So that is the problem. So in this scenario, we can see the vehicles as a communicating devices, and we can see RSUs, which are roadside units, which are basically the roadside units, and they are communicating with each other either with the roadside unit or with the vehicles. Now this shows the vehicle architecture, the basic architecture, how it works. On the bottom, we can see OBUs, which are onboard units, and AU, which are application units. These are basically within the vehicle, okay, within the car or a vehicle that we see. So all these units are installed in the vehicle. Now they have to communicate in the ad hoc network manner. One option is that simply we have a Wi-Fi connectivity among them. Another option is we have the roadside units. Now on the top we can say it is connected to the internet, okay, and with the help of either with the infrastructure domain or without infrastructure we can have. Okay. You must have heard, or you must have read in the news that all these companies, the mobile companies and all, what they are doing, they have got the permission to use the antennas of any other company. Like we have a portability. We have the portability to switch over the connection from one company to another company. Okay. Same thing is happening now in this wireless connectivity also. The already towers installed by any of the companies can be used by any other company by paying some charges or whatever, and we'll be having the devices or the access points, you can say, installed over there on these towers, so that every node, which is a moving node, can be connected to this. I think around in a kilometer or maybe even a less than kilometer distance, you'll find certain antennas installed. So that can also act as a roadside unit. If all these antennas are being used and we fix up access points to that, so all these particular access points can work as a roadside unit for the vehicles which are moving. Before we go to the characteristics part, any doubt, any questions anybody has from any of our centers? We can say they don't have any specific identity. It's not a fixed identity because we are not giving a fixed IP as such. Okay? The vehicles that are coming in a communication network in the vicinity are communicating. Otherwise, if they are moving far apart, obviously they will be out of that topology and they will be out of the network. Yes, that is the issue. How do we manage? Now, if you compare it, that's where the difference between manets and the vanets come. Okay? The manets is, we are talking of the mobile nodes. Okay? They are connected to the base stations. The moment we move, there is a switch over and it is connected to the another base station. Now here we are talking of the totally ad hoc network. Okay? Ad hoc network means we don't require any infrastructure. Okay? Vehicles are communicating with another vehicles. So vehicle 1, suppose you are driving a car, I am at your back, so my vehicle will be a connecting point to your vehicle. We don't require any infrastructure. That is the main concept of the ad hoc network now. For the ad hoc network, you don't require any access point. You can connect the systems in the form of an ad hoc network. We don't require any access point as such. Yes, we need an ID, but that will be identity less, means what? We won't be having a particular IP for that as such. If we are connected, the moment we are out of that scenario, we won't be connected. Ad hoc network concept says that you connect the systems, we don't require any access point for that, it is the utility. Okay, we can connect 4 or 5 systems together, they'll work on an ad hoc network scenario and we can exchange the information. Same way the vehicle at the front, back or sides can connect to each other. But the only issue here would be if we are connecting the systems which are placed on a table here. Okay, 1, 2, 3, 4, 5. They are fixed. They are not moving. Topology is fixed. We can simply say, okay, system 1, system 2, 3, 4, and 5. That will be done. Okay. But in this case, when we are talking of a vehicles, they are not stationary. They are moving. They are not stationary. They are mobile. And that too, they are moving at a high speed. That is the problem. So here comes the challenge. Roadside units, we are talking of only when we don't have a vehicle in the vicinity. They are far away. Then we can connect to the roadside units. But otherwise, it's a completely ad hoc network. Right? Now, coming to VANET characteristics, few we have already covered. Mobility is very high. Okay. Take a city road scenario. We have a speed limit of, say in Chandigarh, if we talk about, speed limit is around 40-50 kilometers. For light vehicles, it is 60 kilometers per hour. For heavy vehicles, 40 kilometers per hour. So, nodes are moving. Mobility is one of the challenge and characteristics definitely of a VANET. Topology will definitely change because as the vehicles are moving, so they are moving at a different speed. You can talk of a heavy vehicle that is moving at a speed of 20 kilometer per hour and another vehicle, which is moving at a 60 kilometer per hour. So there would be a wide difference. After a minute or so, the distance would be too much that you won't be able to connect to them. Okay? So topology is dynamic, it is changing. Predictable node movement. Now what does this characteristic mean? Predictable node movement. Yes. Right. If we are talking of any particular manet, okay, we know the vehicles are, we know the nodes are moving in a random direction. I can carry my mobile and I can just move in this hall, okay, from left to right, from whichever way. Uh, it can be random. Okay, I can go in any direction. It's a omnidirection. I can move in any direction. Now, in this case, vehicles they have to follow a path. Which path? That the road is specified. You cannot go out of the road. You have to move on the road. So if the road is 20 meters wide or so, your vehicle would be moving in this 20-meter range. Yes, but yeah, but still, road is already existing. You know there is a left turn. You know there is a right turn. Okay, that we already consider. We when we do the simulations, what we consider, we are following a straight road path and there would be a left turn, there would be a right turn, or maybe there are traffic lights, but that is predefined. We can always assume 100% vehicles are following that straight road. Okay, probability is 20% would be moving into left side, 20% would be taking the right direction, and remaining 60% will take the straight road. But still it is predictable. It's not that somebody will take the vehicle from that kacha road and will go. Not possible. So that is why it is said that it is predictable, because road scenario is already there. We can very well see how many vehicles would be moving. That we can judge. You must have seen when NHAI is moving some highways and making some highways and all. There's always people who are just noting down the number of vehicles being passed from that route and how many vehicles are turning in a different direction. Okay? So whenever certain flyovers are made, so this thing is kept into mind, that what is the probability or what is the number of vehicle that would be passing this road in a particular time and how many would be taking different directions. So based on that, they decide that we have to make a flyover in which direction, okay, so that it is of help to most of the people. So that is predictable. We can check it out as well. It's mainly linear topology. Definitely one after the other we have to follow.
Vehicular ad hoc network.
Anyone has any question? If you have any query, you can ask, or otherwise, please mute your mic systems. Do we have any query? Now we further come to the characteristics, hard delay constraints.
अभी क्या कह रहा है? Then TTC NICTA blocked you.
Is everyone connected?
Yeah, ma'am, connected.
Yes, madam, we are connected.
Okay. If you have any queries, you can ask. Otherwise, please switch off your mics for some time because there is a disturbance.
Yeah, ma'am, okay, we are not having any query.
Okay, thank you. So I'll continue.
Thank you, ma'am.
Now come to another characteristics when we talk of delay constraints. Now, what do you mean by delay constraints? In the beginning, we talked about one important thing, that the purpose of VANET is safety communication, convey the messages to the vehicles in the vicinity. Okay. So what if a person has to apply a brake? A person immediately at the back of one vehicle has to apply a brake. What will happen? If a person doesn't get the information within a second's time, it is going to crash into the another vehicle. So how much delay is acceptable? That is important. So hard delay constraints definitely says that we cannot accept, rather we are intolerant to any delay as such in the communication, just to avoid any damage. So hard delay constraint is very, very important when we talk of safety communications or safety message delivery. But there are other applications of VANETs also that we will see, further, for which even if there is a delay, it is acceptable. But for the safety message communication, we simply have a hard delay constraint. Another positive aspect of VANET is as compared to MANET, if we say, or as compared to any sensor networks, those who are working on the sensor networks, we always talk of the power constraint. You are doing the same. So a lot of research is being done, how to save power. Okay, so that your sensors can work for a longer time, so they should have a long lifetime. Yes. So but what about vehicles? Can you imagine in a vehicles, will there be a power constraint? Yes, we have enough power. We don't require anything else because vehicle is moving, so whatever power is required to any of the units, we can use that. And moreover, we don't have that sensor network as such where we have kept the sensors at a various location and then we have to see whether they are alive or not. We don't require any such thing. So power constraint is not an issue. So one of the research areas that used to be the main areas in MANETs, has got no relevance in VANETs. So I think 80% of the research in sensor networks is carried on the power constraints. Okay, but here there is no power constraint because vehicles itself are giving energy to all the equipments or the gadgets that are being there. Now, another important point is when we are talking of moving vehicles, topology is changing. Now, a vehicle which is currently in vicinity of the other vehicle which is moving, ahead, will not be the same in next 5 minutes time or maybe in next 10 minutes time. Okay. So if we are talking of a topology or a linear topology and the links, it is going to change. Network has got a limited lifetime. It has got a limited lifetime. Why? Because vehicles are moving. Okay. They are not stationary. So very simple. And another characteristic of VANET is it's a large scale network. Number of vehicles are moving. If you are talking of a vehicles on any particular hour, if you say during office hours or working hours, around 100 of vehicles would be passing, in 500 meters distance in just hardly 10 minutes time. So if we are talking of 1 hour at 9 o'clock or maybe 8:30 to 9:30 time, which is the maximum rush hours where the office working hour starts, so 100 of our vehicles would be passing in just 10 minutes time in a stretch of around 100 or 200 meters even. So we have to connect to all those vehicles, and we have to connect to the vehicles who are moving on the parallel roads, or which would be diverting or taking directions onto the left or onto the right. So that is the issue. So that's why it is said that it's a large scale network. We can have n number of vehicles. Okay? We can take a distance of around 10 kilometers or maybe around 50 kilometers, okay, for the simulations and for setup. So it is a large scale network. Right? Right.
We can't listen you, madam. Jodhpur. No audio.
मैम आपका माइक म्यूट हो गया। एक्सक्यूज मी मैम, मैम आपका माइक म्यूट है।
No.
हेलो मैम, आपका माइक म्यूट है उस साइड।
It is working now.
हेलो मैडम, प्लीज माइक को अनम्यूट कर दीजिए, आपका माइक म्यूट है, आवाज नहीं आपकी आ रही।
Hello.
Yes,
Hello?
we are
जी मैम,
receiving.
clear है।
Okay, fine. So should we continue? Any questions? There was one question put by one of the members, that how we are going to identify the vehicle, which vehicle wants to communicate, whether vehicle on left of my vehicle or right of my vehicle, or a vehicle at back or front wants to communicate. How can we identify? So this question was being discussed. So those who are working in the ad hoc network scenario, if there are 5 or 6 systems connected in an ad hoc network, now how will they respond? How will they come to know which particular system or which particular node wants to convey? So we have ID numbers, we can say, or identities of each system by which we can convey or communicate, and we can see. Like you have a Bluetooth. How do you identify Bluetooth? If I want to connect, how do we identify? By the name. Okay, so we keep the name of a device particularly, okay, so that it is recognizable. Same thing is done with the vehicles as well, because they are moving on the road, so they get particular identity, like we can give in the ad hoc networks. Okay. So similarly, maybe any IP address or maybe any identity we can give to the systems. Names won't do. It is only the numbers, or it is the IP addresses, or not the IP addresses basically. No, no. Then the indication is from which side you are, because topology is fixed. That time when the vehicles are moving together, at particular point of time there is a fixed topology. I'm talking of a discrete event scenario. Discrete event means a fraction of a second. If I see the scenario is same, 5 vehicles are moving, they are in a network, they are moving for a fraction of a second, there will be a topology. Definitely it is a dynamic topology. After a fraction of a second it is going to change, but for that particular time, what we have established a network. Okay. Now this network, that is where the challenge comes. That is where the challenge comes, you know. That is the challenge being handled by different protocols, routing protocols that we do specially for VANETs, not for MANETs. Okay? It's not simply AODV that works in VANETs. Okay? So we have different protocols for that. So then we have each identity of each system. That is why I said that it is only 10% matching with the MANETs. Though the name is, similar, instead of mobile we have only vehicles. Okay? But otherwise there is just 10% similarity, because both are ad hoc networks, but there are changes. Simulations are different because we have to simulate the traffic, we have to simulate the vehicles, which are nodes which are moving. So we need a specialized, simulators for that. We need to have all these specifications. Definitely. Yes, yes, yes. Right, right. Consider a scenario where we are having a Wi-Fi system, and consider a scenario where we have a wired network or Ethernet. Which one will we prefer? Wired? Wired, definitely. And what is the cost involved? Can we have the wired network of all the systems, in this building or maybe the adjacent building and all? Then what we do? Wi-Fi. We cannot have a roadside units installed after 1 meter or 2 meters or 10 meters distance. Okay? See the access point. Maybe you might be using modems at home. Okay? So see the connectivity. It is range is what? Somewhat around 5 meters, 6 meters, 7 meters, 8 meters, 10 meters at the most, not beyond that. Okay? So what if after every 10 minutes, 10 meters, sorry, if we have to, put a roadside unit, see the cost. See the cost. Who's going to bear the cost? The people who are using it. So we wanted to save the cost, okay, by don't putting the sensors and the GPS and all those gadgets over here in the vehicle, but we are paying double the cost by putting the roadside units, which is again a wired, we can say. It's a particular thing. So ad hoc network concept will not help in that case. So that means we are just adding the infrastructural cost to our network, which is not going to serve the purpose. Okay? Because it's a large scale network. It's not a small scale that within a room we have to establish. It is throughout on all the roads. If we have to do, it is throughout on all the roads. Okay? If you see the boundary of India, maybe it's 7,000 or 8,000 kilometers stretch. If it has to be covered through roadside units, definitely it is not possible. No company is going to spend that much amount, and no user is going to pay that much amount for that.
Question from TTC Jodhpur.
Yes.
If you can tell us a few applications of VANET, then it would be easier for us to understand. Second, can you tell us about some simulation softwares which are widely used? And third, I will like to mention that GPS would be ultimately included, because the government will use this type of gadgets to spy on the vehicles, some of the vehicles maybe. So ultimately GPS would be included, and latitude, longitude information would be accumulated, will be used someday.
Yes, answer to your three questions you asked. The first one about VANET applications, I'm already on the slide which is showing you the VANET application. So we are going to discuss that. And about the simulations and all, we have one simulation ready with us that we are going to show to you from the beginning, that how you can simulate the vehicle movement and how it can be done into the network simulator. So that we are going to do step by step once we have an idea of VANETs and all. Maybe a post-T session we can have on simulations only. So step by step you can see all these simulations. And the third one is the GPS system. Now definitely the GPS is required because we have to convert the longitude and the latitude as such. Okay, so for us, for the VANET scenarios and all, you'll see in the simulation that we'll be using the longitude and the latitude of the vehicles that are moving, okay, on the road. So GPS definitely is going to help us out. We are not denying the fact that GPS is not required, because it's the positioning of the vehicle that we require for the simulations and all. Okay, but we are talking of the ad hoc network part, just the ad hoc network part, just to save on the cost of what we are having for the wired connectivity, okay, or for the access point that we need to put otherwise, right? So probably your queries would be more clear when we proceed further onto the slides, right? But
Thank you,
to
madam.
do the simulations, you need to be patient to first understand the concept, and then we'll move on to the simulation part, right? So coming to the VANET applications, there are three different type of applications, or three different areas of applications that the VANET has. First and the foremost is the safety application. Now, what are safety applications? Any information that is related to safety passed on by a vehicle would be a safety application. It can be a collision avoidance or any warning about the collision, that there is an obstruction in the front and brakes are being applied, or there is some road is damaged in the front and vehicle has to slow down. So information would be passed on to the previous vehicles. Okay. Lane changing. Some vehicles want to change the lane or maybe want to move into the faster lanes, then that information will be passed. Navigation. Navigation, again we are using the Google one. But the only problem is when there is no connectivity and when there is no data cards, data packs available with us, then we cannot connect. Okay. So navigation is again going to help out, because vehicles going in the front are going to pass on the message, okay, this is the right route to move into a particular direction or take a particular road. Second type of application consists of a comfort application. Now, comfort application means entertainment. Entertainment can be in the form of that online games that we can play. If 5 vehicles are connected to each other, obviously the drivers cannot play, but the co-passengers can definitely utilize their time in, for the online gaming and all, because they are all connected. Okay, so it is as good as 5 players, connected to each other, or 6 players connected to each other and playing a game. Or maybe we can have the 11 players connected with each other and playing cricket on the online system. That can also be done. Internet access would be easier in that particular case, because how it can be easier? We can get an access to the internet, or maybe you must have heard of the file sharing system. Okay, how do you download movies? How do you download movies from internet? Very crude way that we
Peer to
generally.
peer.
Pardon? Somebody gave me answer.
Peer to peer.
Peer to peer. Yes.
P2P.
Okay. Anyone from academic background, or all are from academic background? Lot of challenges we face, the computer science people or the networking people face from our students when they, choke the network by downloading those movies and all. Any guesses? So torrent is one particular thing that is being used generally, and that has been a great challenge for all of us, those who are dealing with, young generation. So BitTorrent and torrent and all the issues. What is the concept? Basically, it was started with uh, a concept in a mind of file sharing. Okay, file sharing on the net. Now, in a BitTorrent, if 10 people are wanted to download a particular thing, now if I want to download a 10 GB data, okay, I may take 5 hours time or 2 hours or 3 hours depending upon my network speed. Okay? But if it is divided into 10 different people, each has to download 1 GB data. So time would be reduced to 1/10. Okay. And now I have got a volume 1, I say volume 1. Somebody else has got volume 2, somebody else has got volume 3, volume 4, and we have got all 10 volumes downloaded. Okay. Now what we have to do, we have to share one by one. I'll share my data with the other people will say the data with the other people. Now how it is going to give the faster access, because if all of them want to download from a particular server, 10 users want to download 10 GB data from one server, definitely the speed is going to be slow. Now each individual user has got 1 GB data and they want to communicate with each other. What will happen? It will definitely be faster, because now the communication is being done not through a particular server but from the different channels or from the different users. Definitely there are security threats in the BitTorrents or the torrents that are being used, but the purpose of torrent was basically very noble cause to share the information in a lesser time, okay, and to utilize the bandwidth properly and utilize the time properly and to utilize the sharing techniques. But we are trying to misuse it by doing different things with that. Now same thing can be done in comfort applications as well. Internet access, I want to download something, the vehicle moving in front of me wants to download something, the other person wants to download something, it can be a news even, okay. So I download one part of it, vehicle in front download another part of it, third vehicle wants to download another part of it, and then we can share. So we can share all the news, okay, all the videos or news which are relevant for the current scenario, and it can be passed on to different vehicles. So a vehicle is basically acting as a proxy server to me, and it is passing on the information to me, right? Third one is the automated parking services. The third comfort application is parking services. Definitely a vehicle parked will convey the message, okay, there is a space in my vicinity. Okay, come to this particular area, come to this particular site. All of us are facing problem now in parking, because whenever we have to park a vehicle, especially in malls and in shopping areas and all, we don't get any space as such. We have to move around and find and wait for somebody to guide us and tell us. What if the vehicles are giving the information? Okay, so that can be done. Third and the foremost application in which a lot of research is coming up is the commercial applications. Now commercial applications consist of majorly the advertising part, if we say. Okay. Advertising means if I am moving on a highway and I just want to stop in a nearby restaurant or maybe a McDonald's or maybe a Pizza Hut or whatever. Okay. So what I need to do, I need to check it up either from the Google Maps, where is it located. And what if Domino's or McDonald's have got a smart shops or smart points to give the information to the user that okay, this stop is 500 meters ahead. Okay, so this type of a thing is being communicated with the help of a commercial applications. What if I want to purchase something from the market? I don't know where is that shop. I want to go to some shop, maybe a grocery shop, maybe Walmart or any other mall as such, best price and all, whichever malls are there. I want to purchase, but I don't know which are the schemes. I want to buy a LED, okay, or LCD from a particular shop. I don't know what are the current schemes going on. What if, you know, I get the information from a dealer, from a shop or a people that, okay, these are the schemes, and the shop is, you know, just 500 meters ahead. So I don't need to move further. I'll just get the information, okay, there is a shop nearby 500-meter ahead from where I can get my things, and there are good schemes going on. So it is going to help to improve business of the people, those who are into this area. It is going to help me as a customer, okay, to not to, you know, move here and there, check newspapers, find out, talk to people and find out that which is the best deal. I can come to know all the best deals, and I can come to know the locations also as well, that it is, you know, 1 kilometer from my place, it is around 500 meters, it is towards left or towards right. So I can decide and I can take that route and just move ahead. So this is a commercial application. A lot of work is being done in safety applications, but for commercial applications, definitely it is coming up well, because a lot of companies are trying to invest into the research which is being done in the commercial application area as well. Okay. So any queries on the applications?
Yes, madam. TTC Jodhpur.
Yes.
Real-time traffic information can also be passed to the vehicles. This can also be one of the application. And VANET can be used for driverless vehicles. And there can be communication between the drones which monitor the traffic and the cars. And also the parking for the automatic parking system, the parked car, those cars which are already parked and the driver is not inside the car, they will have to keep the VANET on.
Yes. Now, if we talk of the parking services and all, there can be one issue. If we have parked the vehicle, now that vehicle can communicate the message, okay, that, okay, this place in my vicinity at this area is empty. Now, how it is going to tell? Vehicle is not owned, there is no driver as such, okay. So for that particular application, again the sensor comes, okay. Sensors with a lifetime of maybe few hours, which are charged for few hours, for 3 hours, for 4 hours, for 5 hours, for 6 hours, okay. That can be active and that can convey the message. And maybe at the tolling booth, the information is fast, okay. Tolling booth itself is acting as a smart with the RFID cards and everything given to the vehicles and all. It can store the information, okay, this vehicle, park it in this location, in this area, and stay there, okay, right? And the vehicle which is coming at the back, the front vehicle is passing the information ki, okay, I am going to park my vehicle at this particular location. So suppose 3 or 4 vehicles are moving, okay, all are related to each other, they want to park at one location or they want to see the location of each other. So if I have got the location from a tolling booth, okay, I have to park my vehicle at this point, and then I pass it on further to any particular vehicle at the back, that is okay. Before, you know, parking the vehicle, I find out a place as a driver, I find out a place, and then a message is conveyed to the tolling booth or to the vehicles at the entrance, okay, this position or this parking space has been occupied, and then vehicle is parked there and driver moves out. This much information can be parked. If we don't want to put the sensors and all, we can just give the information before parking that this space has been occupied, and same information will be stored in the tolling booth, and further it will be stored that one parking place has been occupied and remaining are vacant. Okay, that can be done, right? Any other query?
There can be more applications. If I'm sitting in McDonald's and I want to know that if there is a taxi car available already in the parking lot waiting for someone, or it is idle.
I'm not getting your voice. Please switch on your mic.
I am saying that there can be one more application. If I'm sitting inside the McDonald's
Yes.
and I can know that is there a taxi car already in the parking space which is idle and waiting for passengers to come. So the taxi car's wallet can give the message to the McDonald's Wi-Fi network, and the McDonald's Wi-Fi network can give it to my mobile device.
Yes.
So while enjoying my meal, I can know that the taxi car.
Am I audible?
Yes, madam.
Hello.
There can be a good application. It is a very good application to know about the vehicles that are parked in vicinity in any of the eating joints and all. This can be done through VANETs, because all the applications that we can think of which can be done with the connectivity, with the Wi-Fi connectivity, can be done with the VANETs, because vehicle is now a moving node which is having a proper network connectivity. Okay. But otherwise, we already have an applications, given by the taxi services like Ola and Uber, which are coming up. We can check the vehicles in the vicinity from that also. That already is there, but same can be done through VANETs also. So VANET applications is not what I'm just telling you. It's a broad application that I've covered over here, but there are enormous number of applications, n number of applications if you see of VANETs, because once we are able to connect the vehicles as a node, so anything that is possible with the network, we can do it with the help of VANETs as well. Okay, but VANET was started with the basic purpose of safety applications. Okay, that is why a lot of contributions, lot of work is being done for the safety purposes first of all. But yes, definitely the other two applications are picking up because companies want to promote these things. They are ready to invest into these things also for their benefit, right? So this is just a glimpse of the applications, but we can have lot many applications of VANETs as such. Any other question?
Hello, ma'am. ये entertainment any example of entertainment?
Any example of entertainment? Okay, one example I gave of the online games that we play with the system. The people who play online games, how do they play? How do they play? A person is acting as one player, computer is acting as another player, or maybe the people who are on the net and want to play the same game, they act as a different players. Okay, so same thing can be done in the vehicles also, because vehicles are connected, so the vehicles moving alongside each other, they are basically into the ad hoc network. They have set up a network. They can be connected to the internet, or they can be connected among themselves and can play. We have the offline applications as such on one system where we need n number of players. So once we have 5 players connected with the ad hoc networks, so we don't require any infrastructure. If the game is there in one particular system, all of them can access and share that. So that way it can help. Or maybe if it is the through infrastructure, we can connect it through internet directly, and the vehicles who are moving alongside can play maybe a game which is again a car racing or so. So when the drivers are moving and overtaking the things, the co-passengers can definitely play the games and can have the feel of whether they are driving a car. Okay? So this is a entertainment. And another can be another entertainment application can be uh, probably you want to watch some videos and all. Okay, so it is not possible while moving on a road. It is not possible sometimes because you are using a data pack, so you cannot connect through your mobile. Sometimes it is not clear. But if the vehicles are moving, the vehicle which is in vicinity of a roadside unit can get an access to the server, can download that thing, and it can be passed to the different vehicles who is requiring that particular thing. So vehicles are basically acting as an access point for the another vehicle which is at the back. So this is again a entertainment application. It is all related to the network scenario.
Thank you, ma'am.
Any other query? Okay, so we'll continue further. I think most of people would be from network background, or maybe having an idea of the network. So we come to the hardcore networking part now, the standards and the protocols for VANETs, how it is being implemented, what are the protocols that have been designed. Okay, so just a quick glance of it. We have a IEEE 802.11p standard for this vehicular environment, that is WAVE, which is wireless access for vehicular environment. This standard is defined. Now it is working on the concept of dedicated short range communication, because the frequency is in gigahertz. Okay, so we can recall the our ninth or 10th standard formula of frequency and the wavelength, okay, which are indirectly proportional to each other. So higher is the frequency, lower would be the wavelength. So that's why it is said it is a short range communication. But it has got specific meaning in VANETs, because we don't want to communicate to a vehicle which is 1 kilometer back directly by a vehicle which is 1 kilometer ahead. We just want to pass on the information from one vehicle to another. So we don't require such a long range of communication. We just require a dedicated short range communication services with a smaller wavelength, so that vehicle can convey information from one vehicle to the back, and further it can be passed on. Okay. Now there is a concept of fading, multipath fading, as well as obstacles that create some effects or the things. For that, orthogonal frequency division multiplexing is important when we are talking of the multipath fading. Now what does it mean? If some vehicle, if a heavy vehicle is moving in front of my vehicle, and another vehicle which is in ahead of that heavy vehicle wants to communicate, so that truck, basically there are two cars, in between there is a truck. Okay, now that truck will act as an obstacle if I want to communicate to the vehicle in front. Okay, so that is an obstacle. For how to overcome that? Now the obstacle, what will it do? If a vehicle in front wants to communicate some signal, it will be reflected and refracted. So vehicle at the back will be getting a signal which is delayed in time from the various directions. Okay? To overcome that multipath fading, we have a orthogonal frequency division multiplexing concept, in which the signals which we receive, they are orthogonal to each other, so that they cancel the interference of each other. Okay, so a lot of people who are doing research on a physical layer or MAC layer have an idea of this orthogonal frequency division multiplexing. Now we have a medium range of vehicles specified as 1 kilometer. We can communicate till the range of 1 kilometer, because beyond that we don't require as such. Okay, because topology is changing very fast, so beyond that it won't be of any use if we are passing the safety messages also. Now if we see the standards on different layers, the lower layers of the VANET scenario follows IEEE 802.11p and IEEE 1609.4 standards. This is for physical and MAC layer. If we talk of the network layer, we have another standard, IEEE 1609.3. All these standards have been well defined and written in IEEE formats and all. So anyone who wants to access that can see the IEEE standard site and can come to know all these write-ups given over there. This is of help to the researchers who want to contribute more into this, okay, who want to pursue their research into different layers of VANETs. Now the transmission range, generally we say it's a dedicated short range, so we say it's generally from 300 meters to 1000 meters, not beyond that. Signal bandwidth that we take is 10 megahertz, because it is divided into different bands. So 10 megahertz is the signal bandwidth. Generally the data throughput specified by the IEEE standard in 802.11p it is 3 to 27 megabits per second. Now we require the high throughput when we are talking of the safety messages. But for commercial messages, definitely it is desirable to have a high data throughput because we want to download something. But otherwise for a safety applications, it is a mandate requirement to have a high data throughput. So data throughput is varying depending upon the commercial applications. Now for the commercial applications, we require high data throughput, which is desired, but for the safety application as well, we want lesser delay and high data throughput. But again, if we see the concept of safety messages and all, this message is definitely going to be very short. Okay, we are not downloading anything as such. We are not downloading any particular thing. We simply want to convey the message, okay, brakes have been applied by the vehicles in the front. So this small message actually doesn't require a lot of bandwidth. Okay? So even if the throughput is less for safety messages, it is acceptable, but delay should not be there. Right? That is important. For commercial applications, definitely speed is required. Okay. The people who want to utilize it for the commercial purpose would be requiring a high data throughput, maybe a larger bandwidth, and again there would be a competition to acquire the larger bandwidth. For safety applications, only the delay constraint because messages are small, so we are not bothered about the high throughput. It's just a small signal that has to be passed. Okay? For the commercial applications, definitely the throughput required is high. So there are certain MAC protocols, CSMA, CA, I think everyone is aware of, those who are working in the networking area, and Aloha, RR Aloha, round robin Aloha for the MAC protocols that we are using. Now, the different type of routing protocols. There are reactive protocols, there are position-based forwarding protocols, and contention-based protocols also that are being used in VANETs. Now here comes the changes with the MANET, because the AODV actually being used widely in MANETs may not be very much efficient in case of a VANET because we have a dynamic topology. So we have another special protocol, that is Wave Short Message Protocol. This is specifically used for safety messages. So this protocol is being used for safety messages. So coming to the routing protocols, different types that we had highlighted in the previous slide. We have certain topology-based routing protocols, certain position-based routing protocol, hybrid-based protocols. Now they have various applications in different areas. Something can be related to the safety message with the lesser delay. Some, protocols may be suitable for the commercial applications where high throughput is required. Something may be, related to the comfort applications where, we need to broadcast everything. So we have a different type of protocols working in different scenarios. Okay, and each one can give different results in different type of applications as well. So we have to choose for a particular application that which protocol is giving the best results. Now there are different challenges. It may be of this slide, 2-3 slides I'm going to cover, maybe of use to the researchers who want to pursue research in VANET area. Certain challenges and the research areas that can be taken up in the VANET scenario. Mobility models is a big issue in VANETs because vehicles are moving at a fast speed and it's very dynamic thing. So how the vehicles are moving, how it can be modeled, because we have a standard models for the MANET scenario, which may not give you the good results, the actual results in case of VANET as well. So research can be done into the mobility models. Another type of a research can be done in the obstruction, vehicular obstructions that we have in the propagation, and that leads to the fading. Another is another criteria is modeling drivers' reaction to information provided by VANETs. Now this is not directly to networks, but it has got various applications in artificial intelligence as well. Suppose message is conveyed to a person who's driving vehicle at the back that apply brake. Now how that person reacts, what is the response time of a person, that also matters. Okay, suppose it's raining. Okay, I'm not able to see the road in front, but suddenly I get a message from the front vehicle that stop the vehicle, there's obstruction in front. So how do I react, in how much time I'll be getting the information, and how do I respond to that particular message that I have received, that is also important. So that comes to the modeling behavior of drivers as well. How fast the reactions, how fast the reflexes of the people who are driving the vehicle. So that is again something related with the artificial networks and neural networks as well. So this is integrated area of VANETs as well as the artificial intelligence. Then we can have networking simulators, the APIs that we can design for simulators, because we don't have any simulator as such which is giving us the traffic scenario, basically a mobility of a vehicle, as well as its implementation in a complete network scenario. We have NS2, we have NS3, we have Omnet, any other Qualnet and all, any type of a simulator, but they are network simulators. They have no module as such which is specifying that how vehicles are moving. So we have to connect to these two simulators, which should be compatible to each other. Okay, so APIs need to be defined for these particulars so that we can have one common simulator for VANETs as such. Another is transmission termination due to sparse vehicle movement. A lot of research is being done in the area when number of vehicles are less. What is to be done? In a midnight, if most of the accident happens during midnight when the drivers are somewhat they are sleepy or something, okay, and they don't get any information, and there are no vehicle in the front, and suddenly somebody says, okay, there is vehicle just 2 meters ahead, because in the dark sometimes you cannot see, and sometimes there is a glare of lights coming from the opposite direction and you can't see. So how that can be taken care of? When there are just two vehicles in a 1 kilometer scenario, how they will communicate? Then what is to be done? That is important. Then we have a optimization of network protocols. Now, in the previous slide, we discussed that there are a number of protocols for various applications. But every time we cannot evaluate the performance of each and every protocol for each and every scenario. The combinations would be too large. So we have to optimize, take the optimized situation as well as take the optimization of protocols that can be used for wide variety of applications in the VANETs. Okay, that is another area. Fading we have already covered. Now obstructions and all we have already covered to some extent. Another research area is the flooding strategies. How to flood the message across. Suddenly there is a road traffic jam, or suddenly there is an obstruction, there is a dead end. Okay? How the message is to be flooded to all the vehicles. So flooding techniques is important because it's a large scale network. So when we are talking of a flooding, that means there has to be a packet loss. So how much would be the packet loss? It should not be such that the vehicles are not getting the information and we are just having 10% throughput. That is not acceptable. Okay? So optimization in those flooding strategies is important. Network fragmentation, hands-off, like you asked me about the hands-off. So that is also a concern. Okay. Now reducing interference with the another vehicles, because it's a ad hoc network, definitely interference is going to be there because they are moving. And then there's a specific research area on the ultra TDD standard, time division multiplexing and duplexing thing. Cross-layer designs are definitely in ad hoc networks. These are much in desired thing, cross-layer designs, so that you have lesser flexibility and you can combine all the operations in one layer. Okay, so earlier we devised network into different layers so that they are independent of each other. Okay, so that if there are changes in one layer, it should not happen that all other layers have to be changed because they are logically independent. So any changes or any additions in one layer, any modifications in one layer is not going to affect another layer. That is the concept of layering. But somehow we want to, have a rigid scenario as well. We want to combine these two layers so that if we have to add something or if we have to optimize the things, we don't have to go to different layers. We have just a cross layer which has, it's a hybrid layer which has the applications of all the maybe 2 or 3 layers which we are combining, and then we find a module, because for every layer we cannot contribute. Okay? Power management to avoid interference is again important, because we don't have power constraint, but we have to manage the power of the communication signal so that there is no interference to the vehicles. Security issues are very, very important. So a lot of research is being done into security issues also, because any message or any intrusion into the network can take the life of people as well. Okay? Economic constraints are there. Definitely we want to make the network cheaper. So certain simulators, which few of the simulations we'll be doing further with some of those simulators, but these are the general simulators. As I said, we don't have any particular single simulator for VANETs. We have to use a combination of a network simulator and the traffic simulator as well. So we have wide variety of options available for network simulators and as well as for the traffic simulators. But we need to see the compatibility. Okay, which all traffic simulators are compatible with the network simulators. For our simulations, we'll be using NS3 as a network simulator. We'll be using Move and Sumo as the traffic simulators for that. And we'll be taking the road scenario using Google Earth and all. So this covers, session 1 of our basics of VANET, though it was more theoretical, but this information was required, to have an idea of VANETs and what are the challenges and what actually needs to be done in the VANETs. Okay. Any queries in the area? Because in next, after, post the session, we'll be having simulations that would be shown on the traffic simulators as well as on the NS3. If everything goes well, we'll be able to show you the complete process. Okay. Any queries till now? Any questions? Yes. 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 Right. Yes. When we talked of characteristics, it was said hard.
Remote centers, tea break. 11:30 is next meet. Next session is started 11:30.
So in the beginning, we discussed hard delay constraint. Now it depends upon the application. If it's a safety application, even if there is a delay in seconds, few of a seconds, so it's going to damage. If it's a commercial, we don't mind. If something is being downloaded.
Hello. Hello. Hello.
Hello.
Hello. Hello.
You are audible. If you have any query, you can ask.
Yes. I am Vibhudendupati from Odisha. So, CV Raman Engineering College, Bhubaneswar. Is there any application related to cloud, mobile cloud?
Mobile cloud.
Yes.
So as such, if we are talking of a cloud, definitely cloud has got a different meaning. We are not talking of cloud as such over here, okay? Because it's not a storage space. We are not storing anything into it. It's only a dock network. cloud. So that is a different thing. That's a difference. But it's a application of a cloud basically. If you want to store something, okay? So it's a different thing. I mean, we here we are not talking of putting anything onto the cloud because we don't want to store information. Cloud can be used when we are talking of commercial applications, when we have to download and store and then communicate to the previous vehicles. Okay? That then it can be used, but majorly it's of the cloud application. When it is just vehicles are being used as a simply node to download something, but then again the issue would be then we have a storage space. We need to have mobile servers, you can say, rather than mobile nodes. We should have a mobile servers basically, right? You can store the data and can communicate further, right? Any other question?
No, thank you.
Okay.
हो गया हेलो फिरोज जी Hello. वो लगा इनके अभी टी ब्रेक हो गया.
मालूम आप पहले से काम करा रहा है. मैं ये बता दिया. वो बंद कर दो. अब ये सही है. आपने याद से नहीं है. 10 पे ये काम नहीं. तो इसमें ऐसी देखिए मैं चला दीजिए 6 तारीख तक पहले और कुछ आज मास्टर ने मुझे दोस्तों से गुप्ता जी क्या है मैं निकल लूंगा ना जनरेटर एक तुम लोग के बाटो में कितना भाई साहब अरे कर लेंगे मैंने साथ में डाली सर आप कौन सा ये जाएंगे जी सकते तो पीछे तो वेक्टर डाल हमारे बच्चे का
Hello, MIT Muradabad. Can you hear us?
हेलो फिरोज जी हाँ फिरोज जी
कोई बात नहीं। हाँ MIT मुरादाबाद है।
सर गुड मॉर्निंग मुरादाबाद एमआईटी से बोल रहा हूँ सर सर पुनीत राय फ्रॉम एमआईटी मुरादाबाद
हाँ पुनीत जी आप है उधर?
जी सर मैं हूँ सर गुड मॉर्निंग पुनीत राय फ्रॉम एमआईटी मुरादाबाद
SCS VM University. Can you hear us?
सर मैं सुन रहा हूँ एमआईटी मुरादाबाद से
ऑन करो।
Hello.
हेलो
Can you introduce yourselves? Right, our director Saab has come here with a guest just to see this facility. Can you
हेलो
please introduce yourselves?
Sir, our participants left for tea break now, WhatsApp now. So, hello.
Hello.
Yeah, Farouz. Hello. Sir, can you hear me, sir?
आएगा क्लिक कर दिया ना, so you maybe they are disconnected. आप डायल करेंगे सर, हम तो लाइव में देखेंगे 10 मिनट के बाद लाइव में.
हेलो एसएस यूनिवर्सिटी सर, अभी बिल्कुल चल रहा था, बिल्कुल सही चल रहा था, इतनी भी आवाज नहीं आ रहा. मैं भी वहां पर गया. SCS University, can you hear us?
No, it's not clearly audible, sir. Hello.
तो आ रहा था. नहीं सर, अभी देखना पड़ेगा. सर इतना आज इतना अच्छा मॉर्निंग में सेशन इतना अच्छा रहा मैम का ना, मीनू मैम का. कल तो भी मतलब सारा कुछ. हेलो 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 हेलो, कैन यू हियर अस? SCS University, MIT मुरादाबाद. मुरादाबाद, कैन यू हियर अस? ये भी साइड में रखो.
हाँ जी फिरोज जी, आवाज आ रही है? MIT मुरादाबाद से बोल रहा हूँ.
ये पूछ रहा है. हेलो.
हाँ फिरोज सर, MIT मुरादाबाद से बोल रहा हूँ, आवाज आ रही है?
कैन यू हियर अस?
No, no, we can't hear.
MIT मुरादाबाद.
हाँ फिरोज जी, MIT मुरादाबाद.
Audio is audible there or not? I don't know. Yeah. I think okay. And to whom I have to contact?
हेलो.
Yeah.
हेलो, कैन यू हियर अस?
फिरोज जी, MIT से बोल रहा हूँ मुरादाबाद से, आपकी आवाज आ रही है?
Okay. No, some of the schools they were interested.
हेलो.
Scientists will tell you like that's one of the year.
MIT मुरादाबाद, कैन यू हियर अस?
हाँ फिरोज जी, आवाज आ रही है आपकी? MIT मुरादाबाद से.
हेलो 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 हेलो. SCS University, MIT मुरादाबाद, कैन यू हियर अस?
हाँ फिरोज जी, MIT मुरादाबाद से बोल रहा हूँ, आ रही है आवाज आपकी? हेलो फिरोज जी.
Yes. हेलो. MIT मुरादाबाद, कैन यू हियर अस?
हाँ फिरोज जी, आ रही है आवाज? आपको आवाज नहीं आ रही?
ओके सर. Remote center. Our remote center requested to you. Director sir is coming here. Hello. Director sir is coming here. Just feedback. Hello. Remote center coordinator.
Okay, okay. I think this is studying talk to me. I think.
Coordinator here is centers.
It is not audible. Just check out. Hello. No, Feroz.
सर सेशन स्टार्ट कर देते हैं. डायरेक्टर सर आए तो चला ही नहीं, पता नहीं क्या हो गया इसको.
Hello. Okay.
Hello,
Okay.
SCS VM Tamil Nadu.
So I think Feroz is expecting me to talk to him.
Hello.
Feroz, is it audible, Feroz?
Hello.
Feroz? Hello? Hello?
Yes.
Can you hear me, Feroz?
Yes. Yes.
I think there's some issue with audio, it seems.
Hello.
Is it audible now?
Yes, sir.
Tell me, Feroz.
मैम QGIS हमारे विंडो वाले पे है QGIS हो जाएगा अगर हम स्विच करना चाहते हैं तो हो जाएगा Am I audible to all? Am I audible?
Remote centers. I'm audible now. Your response, please.
Yes, sir, it's audible.
Okay, so welcome back after tea break. I think all are geared up now. We'll do some simulations and just step by step how we simulate the VANET scenario. Two basic things we discussed for VANET simulations. We don't have any single simulator as such for VANETs. We are having a network simulator and a traffic simulator to simulate, the vehicle movement. We have a traffic simulator, and then for, networking, we have the network simulator. So network simulator that we are using is NS3. There's a specific purpose of using NS3 because quite common in earlier days was NS2. Lot of contributions or lot of research work were done in NS2, but nowadays NS3 is coming up well, and lot of contribution in recent past is in NS3. We have some new modules that are coming up in NS3. So open source community has got one advantage and drawback. It becomes obsolete and it becomes, very active suddenly. So in a network simulator, if we are getting a lot of contributions in a years or 2 years or 3 years time, so that means this network simulator will cater to all the research needs because people are contributing in different modules as such. So NS3 is one simulator where we have a lot many modules which are, supporting different IEEE standards as well. So just a short, briefing about NS3. Now it's a open source simulator, and we are having a scalable. I mean, we can have large network scenario and we can simulate it with the help of NS3. We can add our own packages also into this, and it is reliable. Like NS2, the people who have been using NS2 in past, similarly it is a discrete event simulator. It's open source. Now we have a simulator as well as the emulator both. Okay, so there is a difference in simulator and emulator. Emulator means it can give its own idea. It can emulate the things. All the scripts in NS3 can be written in either C++ or in Python. Okay, this way it is different from NS2. We can have all the scripts in C++ as well, which is commonly used by everyone. We can handle a multiple interfaces on nodes as well. Okay? And all IEEE 802.11 standards and model is applicable in NS3. So this pictorial representation shows in past, 6-7 years how NS3 has gone. A lot of contributions were done in 2011, 2012, and 2013. I could not get data for 2014, but there was a data in theoretical form that how many researchers are using NS3 for different areas. So it's in lakhs. The number was in lakhs. Around a month back, I was just having a look at NS3 users, community and all. So the number of users have grown in lakhs in NS3. So it is coming up very well. NS3 architecture. It supports all the major routing protocols and support IPv4 and IPv6 both. A lot of mobility models, which is random direction, random waypoint mobility and all, everything is incorporated. The NS3 installation is preferably to be done on Linux, but otherwise it can be used with the help of Cygwin in Windows as well, and in Mac OS also we can do that. But most of the open software, the simulators and all, they are best compatible with Linux platforms. So we have a one site nsnam.org. where we can get the latest versions of NS3. We have a tutorial also that is given there in nsnam.org to install and step by step to build, the topologies in NS3. So you can follow that complete tutorial to understand how NS3 is installed. Because installation is going to take a lot of time, so that is why we simply will skip it off and we'll just go to the simulations. There are two different ways of downloading the thing, which is major. Either it can be done using Tarball or it can be done using Mercurial, which which is basically a version control software. So with Mercurial we have a different codes that commands to be given. And with Tarball, the commands are different, but we try to do it through Mercurial. So all the commands are given here. You can just check it up, which is easily available on the tutorial also. Now there are two utilities to build, the codes in NS3. We can use the Python bindings, or we can use the utility WAF to build the modules, because to start with we need to build all the modules that are there in NS3, and if we are creating our own module, then we also have to build that module. So WAF is the utility that we have used to build all the modules that have been given in the NS3. These all commands you can find in the tutorial as well. And if you are a NS3 user, it's always better to join the NS3 forum, so that if any of the doubts or any of support you require, a lot of people are contributing to that, and a lot of people, researchers communities there in NS3 forums. So you can get a lot of help and support, plus you can also help somebody else if you are facing any problem. There's a basic command to test. Once it is installed, the basic command to test is simply you have to run a hello simulator program that is already there in NS3, and you will see that your NS3 is working fine. So I'll simply skip that, because like any other network simulator, we have to create nodes and channels, we have to create a network interfaces, and we have to configure the internet protocol stack, and then we have to define the applications. Now, there are major key abstractions that are used in NS3, which are in the form of the classes or the helper files created in C++. The key objects here are nodes and application channels, for which individual classes have been defined in C++. And we can use those classes, or we can create the instances of those classes, or maybe we say objects in C++. We can create objects of those classes and can use it in our programs. So I'm simply skipping few of the things, because a lot of things you'll find in the tutorial when you install this. Now this is the basic script to check from NS3 simulator. This is already there in examples given in NS3. So you can just step by step check it up to understand how the nodes are created, which particular functions are being used, which classes are being used to create the object, and then accordingly you can set. So the major thing is, first you need to use the node container, because container is one thing where all the nodes will be logically existing. So I'm skipping this also, because this is already given in the tutorial. So we'll simply go to the basic simulations. Now there are few major steps that have to be followed for NS3 simulator. What we did in our simulations, probably if we are able to connect it, some of the steps we'll show you on the simulator itself, but for some of the things which we will not be able to run here on the simulator, we have the snapshots for them, and we'll show it through the snapshots. Okay. So the first step is we have to simulate the vehicle scenario on any particular road. So first and the foremost step is to identify the roads on which we want to simulate the vehicles. So we have chosen one particular road in our simulations, that is in Chandigarh area, that is a Madhya Marg, which is the main road, a highway road we can say. From Google Earth you can identify the nodes or the locations by putting the nodes or the points of the road area that you want to specify. Suppose I want to have the straight road, so I'll put one or two marks over there, or placeholders we call in the Google Earth. We'll put placeholders in the beginning and at the end, just to identify that the vehicles would be starting from placeholder 1 and will go till placeholder 2, and how many vehicles that we can identify ourselves. Now, when we put the placeholders in Google Earth, we get the values which are in degrees. We have to convert it into longitudes and latitudes because we have to represent it into XY coordinates. So we get into degrees, which is the longitude and the latitude part. But for simulations, like we have to do it on the 2D form or the 2D plane. So we need to identify the X and Y coordinates. So for getting X and Y coordinates, we use the utility QGIS, Quantum GIS, okay, for whichever placeholders we have put on the Google Earth, we will be getting the XY locations or the XY coordinates of that vehicle. So it is, pure application of Cartesian, products or the coordinate geometry that we have into this simulation. Okay. So second step would be the QGIS, from where we'll be getting the XY coordinates of all the placeholders that we have got. Now the third step in the simulation would be the traffic simulation. Traffic simulation consists of the simulation of a vehicles, that means showing the vehicles that are moving on the road. And then further we'll have after traffic simulation, we'll have to get the trace files done. Okay, those trace files we'll be using in NS3 for checking the flow monitors. Flow monitors consist of the throughput, delay, and all other end-to-end delay and all other parameters that we want to check for a particular protocol or for our scenario. So we are going to just show you step by step how it is being done. So the first step would be the Google Earth, how to put the placeholders on any particular road that we are taking in the nearby vicinity. So as I told you, step by step we are going to show you the live simulation, and in case where we are not able to do it on the simulator because there may be certain technical issues for which we may not be able to connect directly, then we have the snapshots for that and we have the files just to substantiate that. So I have with me one research scholar, Ravneet. She is going to help me out in doing the simulations and I am going to explain you step by step. Ravneet, we'll open the Google Earth. You can put your chair over here. So first step here would be the Google Earth taking the road in a particular area. So we'll be taking one straight road, maybe a Madhya Marg or any straight road on Chandigarh city. You need to download Google Earth. You can download the Google Earth, but you should be connected to net to get the current scenario. So once you have downloaded, you will get the logo of the Google Earth in your system. You can place it anywhere, and just once you click on the Google Earth, it is going to connect you to the GPS system, and from where you can get the current location of the roads. So just enlarge it. So already we have selected one particular road. So this is a straight road in the Chandigarh, and we have got two placeholders. Now how to put up placeholders there is one location you can see on the top in the toolbox. We have this add placement, place mark, or this placeholder. You have to click to that and then you can add it. Just you can show one step.
Just click this. We have opened with this placeholder, and this is the latitude and longitude points which we need to be changed to be converted in QGIS, that is quantum GIS, to XY coordinates.
Now, one thing important is whenever you are choosing a placeholder, because we have put only two, you may have, n number of placeholders depending upon the road, depending upon, the left and the right turns, or depending upon traffic light. So this simulation is only for a straight road. We'll be showing you another simulation for a traffic lights as well. So on this road, we have taken one entry point. We can name those points also as well for our reference, because we want to later maybe use it for, the node placements and all other files that we need to generate. So we can give the name, and it is going to give you the latitude and the longitude of that point, which is actually on the GPS system. But this longitude and latitude will be saved as such. We can save the Google Earth file with the all the placeholders in the form of a KML format. Okay, this KML format we can open in the QGIS directly, okay? Or we can compress it. Compressed form is KMZ. You can uncompress it, and we can have the KML format for that. Okay. So we have, these placeholders over there. Just come closer. So we see that we have only the longitude and the latitude of these parts. Now we want to convert it into the X and Y coordinates, because ultimately we have to represent the simulation scenario on 2D plane that we can see on the system. So X and Y coordinates are required. For this, we utilize the utility QGIS, Quantum GIS. We'll show you that. Quantum GIS we have installed on the Windows, but we cannot switch off this system and get connected to Windows, because it is going to close the session. So we have the snapshots available. This was the map. These were the 2 points, placeholders that we selected. These are the longitudinal and latitudinal points that were given by the Google Earth to us of the placeholders that we had created. Now, if you open the Quantum GIS, it can be easily downloaded. Quantum GIS is open source. Now, once you download this and just click on the plugins and add to the plugins, when you open it, it gives you an option under the plugins menu, which is georeference, because we want to get the reference point on the geographical location, that is the XY coordinate. So georeference is one of the utility in the plugins that we can use. So after selecting those georeference point,
georeference should be enabled for the work. Then you have to select a raster file. Whenever you have selected the georeference, there should be an option of reference file. From here, you can pick that particular file which you have stored in Google Earth. That should be saved in JPG format. That particular JPG format should be picked up through this QGIS using this.
So there are 3 ways of saving file in Google Earth. One is the KML format that I've already told you. Second is in the simply JPG format of the map that you can get. And the third way of storing is in the CSV format or the Excel format, XLS format that we save. So for QGIS, simply JPG file will also work. We can select the JPG file, which is showing us the placeholders, yellow marked placeholders over that. So once we start the georeference option open and we put our mouse onto the placeholder, the yellow mark, it is going to ask us the X and the longitude and the latitude value. Once we put the longitude and the latitude value in those columns, it is asking enter map coordinators. Once we put those coordinates, it is going to give us the XY coordinate value.
That coordinate value should be in GCP table. That is the table inbuilt in QGIS. And after you click the GCP table, the coordinates which was the longitude and latitude points can be converted in this particular format. Just see here, source X and source Y.
And it automatically comes. You don't have to do anything to get the GCP table. Once you right click on the placeholder and you enter the values of longitude and latitude, it gives you the GCP table as such, and we can enter the values.
This file is also stored at the backend. Whenever you close Quantum GIS, it would ask for the GCP points to be saved or not. If you will click on the saved format, that particular file should be saved in Notepad or in text file or whatever you want, in which format you want. That should be saved with longitude, latitude, and then next points are X and Y coordinates. Then we come to move to.
Okay, so now what we have done actually in these two simulations, we have taken one road scenario by Google Earth. We have put a placeholders, that is the starting point and end point of our vehicle simulation, and then we have got from longitude and latitude, we have got the X and Y coordinates of those placeholders that we have taken. You can get n number of placeholders anywhere you can put, so that you can communicate through those. Okay, so this was the first step. Now after getting the XY coordinates, now we have to simulate the traffic, how the traffic would be moving from first placeholder to second placeholder. So for that we have different tools, that is the traffic simulators we use. One is the Move, and Move with the help of a Sumo tool is going to give you the idea how the traffic or how the vehicles would be moving on road. So Move tool is easily available on the open source. Just you search for a Move tool, and it is you can simply download it, and it's in a Java. Okay, so you need to have a JDK installed in your system, and it is in the jar file format. Once you download it, simply you click on that logo of Move, and then it is going to give you all the scenario. Switch on if you have. This is the PPT we have shown you for Move tool, but actually we have the tool, we can show it to you. So when we start the Move, we have, first screen that comes up, rapid generation of realistic simulation for VANETs. We have mobility model and we have a traffic model. So we take a mobility model because we have to generate a road map topology. Okay. So we select on the mobility model. We get so many options. We'll follow step by step. First thing is the node, how to create node. Now node would be vehicles over here, okay, and the edge. Okay. So edge means we have to take a starting position and the end position, that would be one edge. What type of edge, that is optional, we are not using it, but we can have, edge type of a different types. We have a traffic lights scenario, or we have a 2 lane, 3 lanes, but that we can anyway specify in our further steps. Configuration is map configuration we have to do, because we have to generate certain files through Move. Okay, each particular button that we are having in this application is going to give you one particular file that we are going to use. So the first few are the map editor configuration things. The second one, vehicle movement, how many vehicles would be moving on the road and what will be their speed. Okay, so that can be simulated over here. Third is simulation on Sumo or any other visual tool that we can have. So we start with this. Once we start with this node, so it is asking us, map node editor is asking us, you identify, give the node ID. We can have an automatic ID or we can give our own ID, and then you can give X and Y coordinates. Now these X and Y coordinates we have already got from QGIS. So same we are going to give. We can check the option of a traffic light, whether we have a traffic light on this scenario or not. But here we are taking a straight road, so there will not be any traffic light. We have already one file, open, ready for you. We'll just show it. So the file created would be in the form of node with the extension .node.xml. पेन ड्राइव से ओपन कर सकते उसमें भी So here the ID is node 0 and node 1 we have given, x coordinate 100, y coordinate is say 100 we have taken. Similarly, any number of nodes we can add because we have got the xy coordinates of that locations that we have actually got. If you don't want to do it on the road scenario, you can simply draw it on a piece of paper, just like we have a coordinate geometry. Okay, draw it on a piece of a paper and see the xy coordinate. You can mention the xy coordinate of your own, and then you can give the same values over here. Because here we wanted to do the real time simulation, so we have taken the road scenario as such. So this is how you can do. You can add further nodes, whatever you want. Like I want to add node 2 to it. Maybe a x coordinate is say 200 and y coordinate is say 100. And there's no traffic light, we are not considering. Okay, we can remove or add node, and we can save the file. This will be saved in the format .node.xml. Then we go to the next step, edge. Okay. So now we have to create a edge, beginning and the end, from where the vehicle will start moving and from where it will end. Now each road can have multiple edges. We can divide them into different small parts also, which we call them as edges. Okay. You have edge, right? So edge ID again can be given automatically, or we can give our own number. Here we have numbered edge 0, 1, 2, 3. But if you are having some particular location, say from this Knitter campus to say sector 17 market or nearby market, so you can give the edge ID accordingly so that it represents whenever later you are referring to that edge. It can just tell you from where it is starting, from where it is ending. Okay? So edge NITTR, then sector 17. Same you can write. Now this edge is starting from which node and ending at which node. This is important. Okay? Node means a placeholders that we have taken. So edge will start from one particular placeholder and will end at the next placeholder. Now we have to specify the lanes. How many lanes are there on the road? It can have single lane, it can be a double lane, it can be 4 lanes. We can specify the number of lanes. Speed of vehicles. Now speed of vehicles can vary in different edges as well. Okay. For certain part we can say the speed is 40 kilometer. If you want to change the speed, we can say the speed is 75, because it depends upon area to area. In certain areas, the speed limit is 40. At certain areas, it is speed limit is 60 kilometers per hour or so. So it can be defined. Now priority has got specific meaning when we say that high priority is given to the vehicle, or high priority should be given to a particular lane. So we divide the road into fast lanes and slow moving lanes. So we can give the priority to that. Okay. Now 75 is a default priority. That means all have got equal priority. If instead of 75 I give 1 or 10 priority to all, that means all are having equal priority. But I can say one edge has got more priority. That means vehicle moving, taking that road, will be having the priority over the others. So we save this file. It will be saved as in the format of a help.edge.nv. Help is our name that we have given. .edge.xml is the default, extension. Now the third step in this would be we need to have the configuration. Okay. Now for this configuration, you need to select the node file that you have created. We had created the node file edge.node.xml, and we created the road file help.edge.xml. Okay. So we'll choose those files from here. and then lane numbers, how many lane numbers, and the maximum speed. Now maximum speed we can give it as 40, 60 depending upon the road scenario. Okay. We have not specified any types of edges as such, so we are not choosing this particular point which says that specify the type files. At the end we have to get the data into .net.xml file. That is basically a map configuration file that we are getting. Okay. So we can give the name, specific name to this output file. Okay, we can give a specific name, select the these files and all. Okay. We do that because here this utility will not be working. So we assume that we have selected all those files and we have given the output file name, and then we click onto that. If we click onto that, it is going to ask us any particular file. Right? If we say create, then after creating, after giving the create, we have to save this file in the format of netc.cfg format. Okay? This is another step. We save this file and then further we close this. Now the last step in map configuration is create map. So we open the option of create map. Now create map, in create map, the file netc.cfg that you have just created, you are going to open that file, okay, and then you'll see create. Here it is not working because there was some issue while connecting it to ICT centers. We just lost some of the files. So once you do that, it shows here in the window, okay, that this has been created. This will show you on the PPT. The snapshot will show you on the PPT which information it gives. So many files open. So this was the node file, this was the edge file we created, this was the CFG file we created with the option map configuration editor. Now we have to generate a flow. Now the flow tells us that how we have to begin, at what time the vehicles will start moving, and what time it will end. Okay. So it is in seconds we can give, beginning is 0, end is 1000. Number of vehicles we can already specify on the roads, that how many number of vehicles would be there. So that we can create. So some things we'll show you on simulation. Vehicle movement editor gives us one option to create a flow that we just created. Okay. And turn, it is the probability that in which direction vehicle will turn. Here we have taken a straight road, so it doesn't matter. So we can simply skip it off. Create vehicle. So now in a create vehicle open, because we have to create a vehicle with the speed of a vehicle, what would be the speed and how many vehicles would be there, we do the flow definitions. Now these flow definitions we have already done. Flow file we have already created.
Actually, we are not taking the files. That's why it is showing error. Otherwise, because we have already created all these files, that is the main reason we have to take that earlier file.
We have to take, the net.xml file here in the map file that we have already created. Now, whatever will be the output, that will be stored in the form of a root.xml file. So we give the name, okay, some particular name, and then we can save it. So it is not giving because we have not selected the appropriate file as such. Okay. So you can show it. So this is a snapshot of how we created a vehicles, okay, by taking the file. Now in this particular file, you see in the screen, we have number of vehicles created, which is showing us reading time step this much. So that means how much percentage of a scenario has been mapped basically, okay? Because it is a route file. So how many routes have been defined, how the vehicles movement has been defined. So it is in percentage, it is showing. Once it is complete, the file would be created, which is root.xml file. Now we'll show all the visualization. Now we'll visualize this file, this visualization of all the files that we have created, the root file and the map file. This is done in a tool known as Sumo. Now Sumo tool and the Move are compatible with each other, but with a specific version only. So Sumo 0.12 is compatible with Move. We can do that. Latest version of Sumos are not compatible with Move. Then we have to use a different tool, for generation of these node and root files. Okay. So we have done Sumo 0.12. It is again an open source that can be simply downloaded. So whatever map we have created and whatever vehicles we have created using Move utility, we can just see that simulation on the Sumo. This is the road we created with the two, placeholders. It is showing the same straight road. Now we'll choose sumo.cft file that we had created with the help of a move tool. This is showing us the vehicle movement depending upon the vehicles that we had given. Okay. Number of vehicles that we have given on the straight road, it is showing us those many vehicles in 2 lanes road. Now it will run till the time this simulation closes. The time we have given over there was 1000 seconds. Okay, we can stop in between. Now this is showing us all the scenario. This delay is important because if we give the lesser delay, the vehicle movement would be fast. We will not be able to trap that movement. So it is up to us that how much delay we want to give into this simulation. Okay. So this is a Sumo tool.
One more thing, Move tool is only compatible with Sumo 0.12.3. But if you want to use the latest version of Sumo with Move files, you have to change your files with certain points. Manually, you have to change that files. I can show you the format of that also.
Pad or text pad, all the files. You can just open it directly. We'll show you actually the file created, the XML file created, that is node.xml edge.xml file. We are going to open it on a notepad so that you can see that what information is given in this XML files. Any node XML file. So this was the node file that we created. Okay. It is giving us node ID 1. It's in a XML format, so you can just see, similar notations over here. X coordinate is 0, Y coordinate is 0, type is priority because we had given the same priority. Had we given a different priority, it would have specified the priority number as well. Node ID 2, this is 100, and Y coordinate, whichever coordinate we give while creation of file, do that. Now, instead of using that move tool, we can create by adding into this as well directly. Okay. Move tool is a utility. To create it, we can simply, it's a tabular form, it's a utility in Java given to us. Otherwise, if you want to create a node file directly, you can add on the nodes into this as well. Okay, it will create your node file. Now we'll see edge file. Now this shows us edge ID from which node to which node. Okay, priority is how much. Here we have got a different priority. We have given number of lanes, suppose 1 lane or 2 lanes, whichever you are specifying, that is going to give over here, and speed is in meter per second. Okay, so if we are giving 40 km per hour, accordingly it will be converted into meter per second. So this is what is created into the edge file. We can add any number of edges directly into this file, or we can use the move utility as well to add on the edges.
These files are actually the compatible file with the latest version of Sumo. But if you want to see the particular file that is compatible with 0.12.3 Sumo, that is.
Why we are focusing on version? Because when we are using a simulator, major concern is compatibility. Which simulator will be compatible with which version or which release of another simulator. So that versions are very important. Sometimes you feel that you are lost somewhere and you cannot get the results because ultimately you find that this version is not compatible with the newer utility that you are getting.
So this file h.node.xml is actually the default file, which is basically compatible with Sumo 0.12.3. You can see here node ID is node 0, and in the updated file we have changed some things like xmlns.http. This is the basic today's version compatible format. So we can generate the files from move, but we can change according to our requirement.
So open one file as well. So now we have seen the node file and the edge file. Now we'll see another XML file created with the help of move. We have a root file. Now root file specifies how the vehicles are moving. So it is giving us input. The tag is input. It is giving us, the file, which file we, referred to. It was project.net.xml. Now we created trips, so trips.xml file would be mentioned. Output file, we specified the output file as a root file. So it is giving us in the output tag, output file. Then after that, we see the vehicle IDs on the top. We see vehicle ID 0, departure time is 0, route edge, which edge is to be followed. Now every particular vehicle would be following a different edge. We need to specify that. So this we can given automatically with the help of a move tool, but otherwise this complete file can be created manually, or we can take help of move whatever way is convenient for us. Route edges says that from edge 2 to edge 1, this vehicle would be taking the route from edge 2 to edge 1. Vehicle ID 1 will be departing at time 1 because we have kept a certain delay. All the vehicles are not starting at the same time because they are randomly coming one after the other. So again, the route edges we have taken from 1 to 2. So it's in the opposite direction. Vehicle ID 2 Depart time is again 2. We have kept a delay again of 1 second, and root edge is only 2. We have taken 2 till the end. If we are not specifying the end edge, that means till the end, till the road ends, it is going to go there. Vehicle ID 3, departure time is 3, route edge is again 2 to 1. So this is, if we have multiple edges, then we can, show 1, 2, 3, 4, 5, whatever edges we have got, okay, that we can show. We have, certain simulations for traffic lights as well. So I'll just open the files for the traffic lights we have. So if we have the traffic light files also, you can just see the difference, how it specifies them. PPT. Second one is PPT, simulation on pen drive. Yeah. There's another file, which is showing us a traffic light as well. So another scenario, there are multiple nodes. Now here certain node numbering has been done as 6L, 6R, 4L, 4L. What does this specify? Basically, these are the nodes created on a traffic lights. So once you are taking a straight road and moving towards left, there is a traffic light. So vehicles would be going towards left, towards right, and going straight. Okay. So left side node has been termed as 4L. Okay. Right side has been termed as R. So if it is a node 4, traffic light is at node 4. So 4L on the left side, 4R on the right side, and then we can have, 4 is the actual traffic light, and further, ahead of traffic light, we can take node 5, 6 or whatever. Okay. So in this scenario, there are 3 traffic lights that have been considered at node 2, where the vehicles can move to left, right, and straight to node 3 as well. And then we have a traffic light at, node 4. We have a traffic light at node 6. Okay. So this is one of the files that can be created on the traffic light. While creating a node file, there was one option given as a traffic light option. So that option can be enabled. Node number you can specify of your own. Placeholders you need to specify on the left and the right of a traffic light, and then you can give the same coordinates over here. Okay. Open another file, which is edge.xml. edge.xml. Now this is the edge created. Here edge 1 to specifies, and there are certain edge numberings given. Now edge means starting from which location and ending at which location. So this edge numbers actually specify that from where the vehicle would be moving. If I say the edge number 7th from the top, edge 2L2, that means the vehicle would start moving from 2L node and will go towards the traffic light, that is 2. Okay. So that means it is an acronym. We can very well check from this that how the movement would be there. So this is how you can number your nodes, so that at a glance you can check that vehicle movement would be from which node to which node. Okay. So next is the net file. All these are on the scenario, which is not a straight road now. We are taking a scenario for traffic lights. So I'm just showing you the files. This is a net.xml file that gets created when we are creating a map. So lane IDs are created of its own. Departure time, maximum speed that we have given. Okay. Length of the road that we have taken, this is specified by the placeholders. Shape means it is showing us the values of the coordinates from where it is moving. Okay. Now edge, coming to this edge is node 21. Again the lanes, each edge would be having multiple lanes. Yes, it's a coordinates. Shape means it's a polygonal form that is going to be taken the XY. Yes. There are multiple lanes, lane 1, lane 2, 3 or 4. 2 going in the forward direction, 2 coming back in that direction. So how the map is configured in the form of a polygon. Okay, each polygon. So this is one particular lane from edge 1 to edge 1. This can be defined as a polygon. Okay, so polygon will be having its xy coordinates. Okay, that coordinates are specified over here. If I specify 4 lanes, accordingly, you know, it will be having the coordinates. Right, so multiple edges, whatever we have created, the multiple lanes. So this file would be created, though it is very difficult to see. But if you understand one step, you will come to know that how it is defining each and everything. This also we created with the help of a move tool, and further it can be added manually. Anything can be added into this. And this is the net.cfg file that we created. This net.cfg file from which we created our root file later on. Okay. So it is just having, you know, all the parameters that we had given. So net.cfg file contains all the parameters that we have given. It is not specifying any root as such. So root file is similar to this file that we create, that how vehicles are moving. So all these 2 steps shows that how traffic simulator works. Okay, this is move and the sumo. With the help of move and sumo, we have created the traffic simulation, and that we can visualize with the help of sumo tool. Now the next step is how this traffic simulator can be, you know, turned into a network simulator, or how we can fetch the values which can be fed into the network simulator, because we have to ultimately check the throughput, delay, or packet delivery, or whatever parameters we want to check for our network. So for that we need trace files. Okay, from the traffic simulator we have got all the scenario, how vehicles would be moving. Now whatever packets would be delivered from these vehicles, that we have to simulate in a network simulator by giving certain values of protocols and all. Right, so what are the steps for that? We'll show you. Now there are certain commands to generate TCL files. We have to generate the TCL files, okay, from all the traffic files that we have generated with the move and sumo, and then those TCL files we can use for the NS3 simulations. Okay. So these are the commands. We reach to the directory wherever we go, and then with the help of a trace exporter utility of sumo, okay, we create the files. Now going to the last command, which says that trace exporter.jar. Now trace exporter file utility comes in Python also with the .py extension. It comes in the Java file also. So as per your, you know, usage, if you have the JDK installed, you can use the jar utility. If you have the Python, then you can do the .py. Python automatically comes when you download NS3. Okay, so you can run trace exporter.py as well. So when we call this utility or give this command, now this NS2 we have to specify, because files are created by using this NS2 utility. Trace exporter accepts NS2 only, but all these TCL files or all these files that we create, that is usable in NS3 as well. Okay, because there was no modification done in the trace exporter utility, because all the files created are compatible with NS3 as well. So there are no changes. So still NS2 is being used to create this file. Now it is for the nodes, that is given a net.xml file, the file that we created, and netstate.xml file, that also we created with the help of sumo. Once you run the simulation, this is the, you know, command to create this netstate.xml file in sumo. If you see the second command from the top, it is giving you how to create the netstate.xml file. Okay. It is also with the help of net.xml file and root.xml file that you had created using the move tool. Once you have created netstate.xml file, now net.xml and netstate.xml file can give you three basically TCL files. Here we have given only two because we required only two. Third one is also given. One is the activity.tcl file, then mobility.tcl file, and third one is the config file, the TCL file. Okay, so these are the TCL files. Now this is giving us the probability. This is giving us the beginning time, and this is giving us the end time that we want to get. Okay, so once we generate all these trace files, okay, we save it for our usage in NS3.
One point that should be noted here is this minus P1, B and 0 and at the end, that is 1000. That should be noted. This number can be changed because whenever we want to create our TCL files, it basically generates the moving nodes. These nodes should be appropriate as per our requirement. Let's say I want to generate 100 nodes in a particular scenario. Sometimes if I'm taking 316 instead of 1000, it will only create 60 nodes. It means our file is incomplete. It's not appropriate. For that reason, we can change this number. And this is these commands are basically compatible with 0.12.3. But in another format, if we are using current scenario and current versions, we have different commands for the same, where we can use trace exporter.py version.
Okay. Once we create these TCL files, okay, we can simulate it with the help of NS3. Okay.
Same commands for current version. There's a small difference. You can check here in the first line. Sumo file.sumo.cfg is used, which is also generated through move tool, as well as some other tool you can use. And fcd output, this is just fixed output. This is the particular command which we will going to find in any module of sourceforce.net. And then again for the activity mobility as well as configuration file, the same penetration rate is given, and 0 to 100. This is similar to the previous one, but the main difference here is we need two files, that is trace XML file which is generated earlier, and the net file. These two files should be placed where the trace exporter.py or trace exporter.jar is there. Because we are using these two files as an input files, and we generate output files as activity, mobility, and configuration files, right? For that particular reason, these two files should be copied at the particular location, or we can give the path for that. That's up to us. What the easiest way for us to do the work.
Do we have TCL files?
Yes, we can generate even right now if you people want.
We'll do it. This is NS3.23 version. If you see NS3.23, one thing of importance is NS3 will be having latest versions also, but you have to download only the stable version. If you see all the releases of NS3, it would be mentioned that this is a stable version. So latest stable version, if you want, you can download that, because if you're downloading unstable, they may not support all the utilities as such. Okay. So if you see NS 3.23 directory, we have bindings which are Python bindings. Then we have the build. If we open the build, we have a lot of files available. This helps in building the modules that have been given in the NS 3.23. Doc file contains all the documentation as well as the tutorial for NS3. You can check it up. Deoxygen is the documentation that is available in NSNAM, website, where you can see all the class structures, all the modules. Now this consists of examples of coding, certain codings. If you want to simulate something, this gives you an idea. Scratch is one folder where we copy all our files. The TCL files that we had generated, we copy it into the Scratch folder, because while building and running, we run it through the Scratch folder itself. Now this is the source file. This contains all the modules of all the protocols or everything starting from physical layer to the application layer that you want to utilize. You can add your own module here itself, okay, but then you need to build that. For example, this is AODV. So AODV has been implemented in NS3. So you'll find all the documentation and examples of AODV. All these are the helper files. Come to the Scratch, which is the main folder. So all the TCL files that we created, we'll copy into the Scratch folder of NS3. Now this file is the activity.tcl file generated with the help of Sumo. It is basically giving us all the information that at which point it is vehicle is starting, at which point it is stopping. So these are the times given in there, and which is the ID of the vehicle generated. So this is the file. Config.tcl files gives us all the configuration, start time, end time, how many lanes, okay, and floor size. This is automatically, or we can define our own floor size as well. Now the mobility gives us the mobility of our vehicles. So it is giving us all the destinations, which node. Now node numbering is automatically defined over here because we are not having a limited number of our vehicles. It is going to continue for 1,000 seconds. So number of vehicles would be moving in those 1,000 second time. So say these arbitrary numbers are given to generate this mobility file. So all these three files we generate, and then these three files are used to get the simulations. Now what result we want, that is flow monitors. We call it as a flow monitors in NS3. Okay, so these flow monitors can be checked, which consist of throughput, packet delivery ratio or delay, and all these can be, these are the major parameters that can be checked. One module is already there. With the help of that module, you can make your own programs and you can incorporate those things which are available over there. Simulation. So we'll show you this simulation on NS3. WAF is the utility to build the modules that we have added or created. So IP1 is one C++ file that we have created and we have put it into Scratch. So it is actually doing the building. Once the build is finished, it gives you the message that it has been successfully done. Now flow monitor statistics give us all the information that we want to retrieve by our network. Now this IPv1 file basically is the C++ programming file. We'll show you the coding as well. So flow monitor statistics that we have specified for our simulation is we have given the source address and the destination address, throughput, how much throughput it has given to us, okay, how many transmission packets were sent, 10 packets, received packets were only 3, delay of 0.723574 seconds, packet delivery ratio has been calculated. Okay. Now the flow ID was from source address this to destination address this. Now this is one two-way communication, okay, from one source to destination and again from back to the another node. Okay, so while traversing back, the throughput is 21.247 kbps, transmission packets, receiving packets, and delay is this much, and delivery ratio is given. So this is how the simulations are done. Now this IPv1 file will show you the coding of this, what it consists of.
One thing you should be very careful using flow monitors. That when you are using flow monitors, there are two methods: flow stats and flow probe. When you are using flow probe, it means you are individually taking the readings. And when you are using flow stats, it means you are taking the readings of whole network.
Now this is the file, the C++ file that we executed in NS3. Now we have to include certain modules which are inbuilt modules in NS3. So it's a C++ file, so some of the coding you'll be well conversant with. Main program is there. We'll come to the actual how we create nodes and all. We'll skip all these things. Now we have created 30 nodes, say 30 vehicles. This simulation has been done for 30 vehicles. So node container is one class. We have created the object of that class, and then a create method has been used. So c.create. We have created 30 vehicles. Then Wi-Fi helper is a class because it's a Wi-Fi connectivity. So Wi-Fi helper class, we have created one object, and we have to enable the log components. Log is important if you want to refer to your results later on. You can check from the logs. Now here it is, standard is 802.11b, which is AODV standard that has been taken. You can check it with different protocols also, because the throughput is low. If you are checking it, you are using a different protocol or you are designing your own protocol, definitely the throughput should improve into that case. So that means AODV has worked well in a managed scenario, but it is not giving a good throughput in managed scenario, the scenario that we created of a moving vehicles. Now, see the top line, we have to set the channel, because once we have created a node in a node container, we have created a Wi-Fi helper class. Now we have to establish a channel. So again, a Wi-Fi set channel method is used to create the channel. Here we have given the IP address. Okay, the base address is 10.1.1.0. You can give your own base address if you want. We have specified the address to the vehicles, basically that this would be the communicating vehicle and this is the subnet masking, so that you can change accordingly. Number of vehicles you want, how many vehicles you want, whichever base you want to set, you can change it accordingly. Now this IPv4 address that we have generated is to be assigned to the devices that we have connected. Which devices? Basically the nodes, the vehicles that we have created. So each vehicle would be assigned the IP address. Okay. These are our comments, so we are just skipping that.
Here we are using UDP Eco Server application. You can use any application like on-off application for generation of traffic. For generating a traffic, we are using UDP because flow monitors are best suitable with UDP. As you can see in the output that just show me this one, like source ID is 10.1.2 to 10.1.7. This is actually from the coding. Here I am writing C from this one. This one. I'm getting the node number 6. It means its IP address is 7 because we already defined the base address, which earlier ma'am told. Sorry. Base address was okay. Then I.get address is the interface through which the communication can be held, and get1 is the node number through which the two nodes which are communicating with one another. And this is the simulation time. Application starts with a particular time. That's up to you how much time you want to give. Here is the animation. What we are created as the number of nodes in the particular lane, right? First, actually visualizing that particular thing, We want to see how nodes are moving, how nodes are communicating. Then there is a net animator inbuilt in NS3. For that particular point, we have one line, one code line, that is this animator, this animation.xml. This is the particular line. Animation interface, nm is the variable object name, and animation.2.xml is the file name which would be generated once the file is built. Then this is the flow monitor.
Now again, the flow monitors is basically, it's a class already defined, flow monitor helper. We can take the help of that class, or if we want to add, certain more parameters to check, we can add it into flow monitor as well. So with the help of a flow monitor, we can check that how many packets were transmitted. You see here Rx packet sum, how many packets were received, and total delay, and how many packets were transmitted. Now this is going to give you the complete coding that like in C++, logic that we can create, that how many packets were transmitted. Just keep on adding that and you'll get the final output. Now we have to calculate the throughput, that means the received bytes, total number of bytes multiplied by 8 to convert it into bits, and then the total time that was taken. So we'll apply the general basic formula for a throughput, and we have got all the values for this, time as well as the receiving packets. We can get the throughput for that. Similarly, the delay and all parameters we can get from that. So at the end, like we destroy the object in C++, we destroy the simulator object created to that, and we return back. So this is the basic file. A lot of comments are there because of our utility, because we try to do different things with that. So that is why certain things have been given as a comment. So this is the basic thing: create a node, establish, connect a channel to them, give them some IP address, let them communicate, check the flow monitor parameters, and then you can find it out. You can see the results. Okay. So now we'll show you the net anim, that is actually the animator of NS3, which will show you that how the nodes are placed. Earlier we see one animation of sumo, that how vehicles are moving. Now this is the animation from NS3, that how nodes are communicating, where they are located. When you download that, NetAnim utility is automatically downloaded along with NS3 itself.
In the coding, we have described the file animation2.xml. Here is the created file. After some time, these red balls, these are actually nodes. This will start moving because I have shown this simulation at a very slow pace. Just see on the board, see on the screen that is fast and slow. Because this is on the slow pace, that is why the nodes are moving very slowly. When the nodes start moving. This is the main thing what we have done in the coding. Whatever the nodes we picked, and during the sumo files and the straight lane, all these things. You can visualize here in NetAnim. But you must be careful about the version of NetAnim. It should be appropriate according to your NS3 version. Like in this, we are using NetAnim 3.106. And if you are using the previous version, the files automatically the file generated is in 3.106 version. Otherwise, it's in 3.104, which is not compatible, even which will not going to show these results.
So that completes our simulation. So just to summarize, because it seems it was a heavy session with a lot of coding and everything, even if you are able to get 10% of the things, so rest 90% you can get without any worry. So you need not worry about, all these simulations and all. So I'll summarize so that you can recall immediately. First step was from Google Earth, you can take, the placeholders or the road, pick up the road that you want to, simulate for. Or if you don't want to take the real road scenario, you can simply specify the XY coordinates and directly can, run move as well. Okay. So from Google Earth, we put some placeholder on a straight road. Then we got a longitude and a latitude, and we utilized the utility QGIS to get the respective, coordinates, XY coordinates along for that particular longitude and latitude. After this QGIS, utility, we started with the move. Now, with the help of a move, we generated node files, we generated edge files, we generated, net.xml file, we generated the root.xml file. All these files were generated, which actually simulated the vehicles that we had identified and specified. Okay. Then after this, we visualize this, whatever scenario we have created of a road and the moving vehicles, we visualized it using Sumo. Okay. With the help of a Sumo, we converted this, into the netstate.xml file, which was used to further, create .tcl files. Okay. So after that, after taking this Sumo files and net.state XML file, we use the trace exporter utility to generate TCL files. So these TCL files we could use in NS3 simulation. So basically what we have done, the vehicles that we had simulated on the road, all this scenario, we had captured it into the TCL files, and the TCL files were further, run into the NS3 simulator, and which we visualized, in NetNM, the movement of the vehicles, how they were communicating, and further we checked the flow monitors, the throughput, the delay, and whatever parameters that you want. We just assess that. You can do it for different protocols, you can do it with different parameters, you can check it with the different mobility models. Okay. At every layer you have various, utilities available in NS3. For example, you can have, different fading models, you can have a random waypoint mobility, you can have, Manhattan type of a mobility, any type of a thing you can vary and you can check it out. And if you have your own scenario, own module, you can add it into the source of the NS3, okay, that you can build, and with the help of WAF utility, like you build any other modules. So once you build, your module is also incorporated, and same module you can fetch and you can use it, your CPP file that you had created for the simulation. Okay, so this is how actually it happens. It's not at all difficult, but you have to be patient and you have to, be friendly with the simulators first of all. So read all the tutorials, go through all the details that are available, and then step by step you can follow it to run all the simulations. Okay, so that completes our session. I know it was heavy session, but most of the times what we do, we simply, skip the simulation part and we cover the theory. So this was important to tell you how actually step by step it is done. So if you have any queries, we can answer that queries now, or otherwise, you can refer to us later on if you have any queries, or better would be to join, the user groups of NS3 or Sumo, or Sumo user group is there, as well as NS3 Google groups are also there. So we can connect over there as well, with other researcher community. Any queries? Do we have any queries? I hope it was not a very heavy or boring session. Okay, then we close this session for now.
Hello. This is from JIT Jodhpur.
Hello.
Hello. Am I audible?
Yes.
Yes. Ma'am, this is from JIT Jodhpur. I have a query. Actually, I have a doubt. Like suppose if a vehicle is moving into an area and if in case of multiple edges, if I do not specify the end edge, then how will we track that vehicle that it is going to reach to its destination?
Can you just repeat the question because your voice is not clear?
Yes, surely. Suppose if a vehicle is moving into an area network and in case of multiple edges, if we do not specify the end edge, so how we are going to track that vehicle that it is going to reach to its destination?
You are talking of edges. What I could gather, just I'll explain that. Then you can let me know whether I have answered your query or not. When we are taking a different edges, suppose vehicle is moving from edge 1 to edge 2. It's a straight road. We have put 5 edges on a straight road: 1, 2, 3, 4. Now edges from starting point to end point. So we have got node 1, node 2, node 3, node 4, and 5. Okay, so node is basically a placeholders I am talking of here. So edge would be from 1 to 2, then from 2 to 3, from the beginning point to the end point. If we are specifying that the vehicles are moving from edge 1 to 2, 3, that means vehicle would be moving from node 1 to node 3. Okay, the first point or the first number in the edge definition and the last number in the second edge definition. So edge 1, 2, then edge 1, 3, then edge say 2, 3, and then edge 2, 4. So if we specify edge 1, 2, and 2, 3, the vehicle would be moving from 1 to 3 location. Okay, if we are specifying edge 1, 2, 2, 3, and then 3, 4, it will be moving from 1 to 4 location. Okay, if we don't specify 1, 2, we simply say it is from edge 2 to edge 3. Now the vehicles would be created in the simulation in between. Okay, they will add in between. Now this scenario is helpful in a traffic light or when we are having some turnings. Okay, there we can say that certain, because we have taken the road as a straight road, but there are certain vehicle on the left and the right side roads which are adding to the straight road vehicles. Okay, so in that case we can specify, okay, ki node 2 to 3, which covers the side lanes also and the roads also, crossing roads also, the vehicles would be added to the main road. Okay, we don't need to go into the side roads or the cross roads, but we can simply take the scenario and we can say that vehicles are being added from both sides, from the left as well as from the right. But that you have to visualize that how you are making your scenario. That is why we say if you are taking the actual road scenario of your own city, you know that it is a single lane, double lane, or it has got a side lane, or it has got crossroads, or how many roads are connected to it. So that way you can define the edges for that particular vehicles. I hope I am able to answer your query.
Yes, ma'am. Thank you very much.
Any other query? Any question, any doubts anyone is having? Okay, I am sharing my mail ID. In case you have any queries, you can connect to me. So you can connect to me at my mail ID if you have any query, because I know unless until you try it yourself, the questions will not come. So it's better those who are interested into VANET areas can try these things, and in case of any queries, you can get back to me. Session was useful to all of you. So we all researchers who are working on a VANETs will get connected through groups or probably directly so that we can help each other. So all the best to all of you. Was it okay?
Remote centers in lunch break. 1 to 2.
हाँ बस सर कर दिया
TTC जॉब सर।
Yes, sir. Yes, sir.
सर मैंने अपनी ईमेल आईडी पर्सनल मेल आईडी लॉगिन की है प्लीज, ठीक है,
ठीक है
इसमें
सर।
बाद में इसको लॉग आउट कर देना। बट टेक्निकल इशू है कोई, वो चेक करते हैं उसमें TTC वाला आपका क्यों नहीं चल रहा। बट मैंने
ठीक है सर।
पर्सनल अपनी ईमेल से आपको लॉगिन करके दिया है।
जी
ठीक है सर।
जी बिल्कुल सर।
ओके
थैंक यू।
Good afternoon, everyone. Today I am Rupali Punch. I will be delivering a lecture on wireless body area networks. Good afternoon, everyone. I am Rupali Punj, a research scholar in Department of CSC. I'll be delivering a lecture on wireless body area networks. So, first of all, we'll go for the background, what lies behind the wireless body area networks. Then we'll see the motivation why we need wireless body area networks, why there is need, what leads us to wireless body area networks. Then there is an introduction to wireless body area networks, their architecture, components, protocols, characteristics, advantages, applications, and finally major research trends in W bands. And what if we integrate the two emerging technologies, cloud computing and W bands? And finally, we have a small practical demonstration of wireless body area networks. So for the background of the wireless body area networks, we have a wireless body area networks are actually formed of sensor nodes. So first we have a brief idea of wireless sensor networks. We have a brief idea of wireless sensor networks, how wireless sensor networks are formed, and the basic working of the wireless sensor networks. So wireless sensor networks are actually formed by deploying the sensor nodes on the region which we have to monitor. So we deploy the sensor node, monitor the environmental and the physical conditions, and then we pass the data to a sensor. Basic working of the wireless sensor networks. The encircled region is the target region in which we have to monitor. This we have deployed the sensor nodes, and these sensor nodes then sense the data which we have to monitor, and they send the data to the sync node. From the sync node, the data is sent to a particular server or user through the internet. So, but in this definition of wireless sensor networks, there are few terms which we need to understand. First of all, we must know what is a sensor node. So, a basic sensor node is a VLSI chip on which we have done some processing, and it senses the information. It senses the information. What kind of parameter we are going to sense, that depends upon the particular type of sensor node. And sensor nodes may be homogeneous or heterogeneous depending on the application in which we are using it.
And there's basic working of sensor node is to sense, process, and they send the data. So the performance of the sensor nodes is continuous. They continuously sense the data, but at the expense of what? They must be losing something. If they're continuously performing something, they must be losing something. So at the expense of and their energy, they are doing something. They are performing their activities. So they are continuously losing their energy. That is, they have a limited battery lifetime, and that too they are losing it. So if, for example, for a wireless sensor network, a wide region is chosen, and then we have deployed the sensor nodes, and continuously sensors are sensing the information, and one by one they're losing their energy. So if for till a particular threshold level, the energy is okay, they find that the sensors are working well, but after, if the energy drops below that threshold level, then what happens? Then the sensor node is considered as a dead node. That means it will no more work as it is intended to do. So if for a wireless sensor network, if the number of dead nodes are increasing in the network, it has a direct impact on the network lifetime. So if the sensor nodes are increasing, the network will not work. So this is the basic issue with the sensor node, that they lose their energy very soon. So basic example which we see in our day-to-day life with the sensor nodes is the we come across many sensors. We wake up in the morning and we use our mobile phones, and we have touch sensors. The touch screen is a sensor. And then we go to a shopping mall. We have many, we come across many automatic doors. Those doors they have the sensors are deployed on the doors, and they sense the information. Then the door opens and it gets shut. So these are basic sensor nodes which we come across. But the thing is, like, where we can relate back the usage of sensor nodes, or the from where it began. So this is in 1950s. We relate back the wireless sensor networks to 1950s. In 1950, US military developed a wireless sensor network to detect the Soviet submarines, and they use acoustic sensors. They send the sound waves from a submarine to in the ocean, and if the sound gets reflected back by if an object is in between the path of the sound wave and it gets reflected back, they can judge that some object is present in the path. They were able to detect the Soviet submarines, and this system is still in work today. But they are used for detecting the undersea activities, so the wildlife and the volcanic activities. But the research didn't started from 1950. The basic research of wireless sensor network came in it is in process since 1980. Since 1980, the research is being done on the wireless sensor networks, and there are many issues still pending with the wireless sensor networks, in which we still have intensive research. So next comes the applications of wireless sensor networks. So in this figure, it shows the applications in which we can see that in our day-to-day life we are using sensors. For example, we start from our homes or buildings, we can say. We can convert them into smart homes or smart buildings by using a lot of sensors. We can have sensors at doors. We can use heat sensors, light sensors, water sensors, and they can detect a lot of things for us. And for example, when a person moves out of the house, we can have sensors on our automobiles, and they can help us detect the traffic route, which is a route which has very less traffic. So all these things can be monitored by the sensor nodes. Next application can be area monitoring, in which we can monitor a particular area in which we have deployed the sensor nodes, and the sensor nodes can sense any kind of information. For a particular area where there are very harsh environmental conditions and the human presence is not actually feasible, we deploy the sensor nodes, and then we can sense the information regularly. And then next usage is the environmental monitoring, in which we can detect the air pollution. For air pollution, there are big cities like London or Brisbane. They have actually deployed the sensor nodes, and they check the concentration of gases in the air. Next is water management, in which we can check the quality of the water or the underground water level for drought. This is very useful for drought hit areas. And then we can also detect forest fire. If we deploy the sensor nodes in forest fire, forest land, they can detect the forest on the basis of temperature, humidity, or the concentration of gases in the forest. They can detect the forest fire, and by the usage of these things, we can actually make a make a conclusion that we can save our people or population from these disasters if we deploy these kind of sensors everywhere. We have industrial monitoring. With the help of sensors, we can monitor the civil structures. The bridges can be monitored, what kind of how much weight they can bear. We can judge these things. And agriculture monitoring is very useful these days, because we can monitor the nutrients of the soil. We can check for the pests and the insect attacks, what are being done on the, all these applications are actually can be related to the Internet of Things. Next comes the motivation for wireless body area networks. Like, we need sensors in healthcare. Why is this being done? Why we need these things? What is the problem with our traditional healthcare systems? So the major reason for this is like the changing lifestyle in which we are having. We are having a sedentary lifestyle with no physical activity. So that is the cause for many diseases. For example, according to the survey of World Health Organization, 30% of the 30% of all the deaths are due to cardiovascular diseases. 180 million people are affected by diabetes, and 2.3 billion people will be overweight by 2050. So all these are due to the sedentary lifestyle. So what we need to do is, and these people, they do not actually reach the doctors. They cannot reach the doctor. Some cannot afford the doctor. Some are unable to reach the doctor. For example, we have lot of traffic on our roads, and the ambulance is going, and we have observed that nobody gives part to ambulance. So the patient who is ailing needs to reach the doctor as soon as possible, but he's delayed due to traffic. So if we with the usage of technologies, with the recent technologies, with the usage of recent technologies, we can develop a system where all these patients can deal with the doctor by sitting at home. They need not visit the doctor physically. So what the goal of wireless body area network is: ubiquitous and affordable healthcare. Ubiquitous means it is present anywhere, anytime the person is available. So the patient who is on the body of the patient, we have deployed the sensor nodes, and the sensor nodes, they sense the information, and it is sent to the doctor, where the doctor can prescribe the medicines, and he can access the information. And moreover, these healthcare systems are affordable, because the only thing to be hardware to be purchased is sensor node, which are not too expensive. And each person is using a smartphone, or each person is using internet connectivity. So we can say that internet connectivity is no more a challenge. So so these are easily affordable, and they can actually change the way we integrate the health technology and information technology. Next comes the introduction for wireless body area networks. Wireless body area networks, they consist of they are actually formed by deploying sensor nodes on the human body, and they constitute of low power, minute, and intelligent sensor nodes. By low power, we mean that they don't require heavy electrical signals to work. They don't require they are not so expensive, and they require less battery. They can work with less battery. Minute means they are small in size. They must be small in size, because human has to carry them every time they move. So their size is a very important factor, and it must be small. Next is intelligent sensor nodes. They can be referred as intelligent We'll start with the introduction of wireless body area networks. They are formed by deploying sensor nodes on the human body, and they constitute of low power, minute, and intelligent sensor nodes. By low power, we mean that they don't require a high power electrical signal on which they can work. Minute means that they are small in size, and they must be small because humans have to carry them all around. And by intelligent sensor nodes, but we mean that they do all kind of processing. They can sense the biological parameters, so they are referred as intelligent sensor nodes. And the basic work of sensor node is to continuously monitor the biological parameters, physiological parameters like uh, body temperature, blood pressure, ECG, EMG, uh, blood glucose level. They can measure heartbeat. They can measure all these parameters. So what happens is, when we have deployed the sensor nodes on the human body, they collect the information. They collect all these parameters for which they are intended to. For example, we have different sensors for ECG, different for EMG, and they collect the information. Then they send to the server, or the we can say a mobile node of the patient. And from the mobile node, the data is being sent to a server which is accessible both to the patient and the doctor. The doctor can access the information and can give the real-time feedback. So this is very useful because if the patient cannot move to the doctor, if he while sitting at his home can be treated. The doctor can alarm the family in case of an emergency, and this is useful for old age patients, for pregnant women, and chronic patients who it is difficult for whom it is difficult to move to a different place. So the sensor nodes can be, in case of W-band, sensor nodes can be either implanted or wearable. By implanted, we means that they are embedded inside the human body. They can be, if we make a cut and then embed inside the human body, or they can be or they have to be or they can be surface mounted. They have to be in touch with the skin of the human body. And wearable, we mean that they can be humans can carry them along. They can be wear on a shirt or on a pocket, or in accessories like tie, belt, wristwatches, on rings. They can be worn and they can sense the information. And there are many sensor nodes for sensing the different biological parameters. And the wireless connectivity of these sensor node is made by a few technologies, which we'll be covering later. And with the help of these technologies, this information is sent to the mobile node. And from the mobile node, using the internet, the information is sent to the doctor. And the basic funda of wireless body area networks is that they focus on prevention. They actually follow the proverb that prevention is better than cure. So they focus on prevention rather than illness. They focus that the patient should not get ill. As the information reaches the doctor can prescribe the information very well. So this is the basic diagram of the wireless body area networks, in which we see a patient on which the sensor nodes are deployed, and the sensor node sends the information and then send the data to a home computer, in which that computer can be any personal device of the patient, and through technologies, and then from the this server, the data is sent to the server which is accessible to the doctor and the patient. This is the basic working of wireless body area networks. Next, we come across differences between wireless sensor networks and wireless body area networks. In this, the basic difference is that the wireless body area network sensor nodes have to be different because they have to measure biological parameters. In case of wireless sensor networks, they can sense environmental parameters like temperature, pressure, heat, humidity, or they can measure motion. But in case of body area networks, they have to measure biological parameters, so their processing is little different from rest of the sensor nodes. And these sensor nodes, they have to be fewer in a limited space. On a human body, there can be only 4 to 6 sensor nodes, and for a wide wireless sensor network, we need to have a huge large number of sensor nodes. And the size of the sensor node is very important in case of wireless body area networks, because the humans have to carry them, so they must be small in size. There is no data redundancy in case of wireless body area networks, but there is data redundancy in case of wireless sensor networks. For example, in a region where in case of wireless sensor network, we are discussing it. We have 2 sensors that are deployed in a region, and the sense radius of these 2 sensor nodes, they overlap each other. The basic feature of sensor node is that they have a sense radius, up to which radius they can sense the region. And if the 2 sensor devices are so close that their sense radius almost overlap each other, then they sense the same kind of information. So there occurs the case of data redundancy. But in case of wireless body area networks, like a sensor of ECG will measure ECG for body temperature, we have different sensors, so there cannot be an issue of data redundancy. But at the same time, there occurs the issue of data loss. Information can be lost. For example, ECG sensor is sensing some information and they are sending it, but if a packet is lost or dropped, the information has to be retransmitted, which is very difficult in case of sensor devices, as they have less memory. They don't keep the information much longer. So these are the basic differences where implanting or replacing the sensor nodes in case of W bands is very difficult. It is difficult in case of WSNs also, but more difficult in case of W bands. These are the basic differences. So we move on to the architecture of wireless body area networks. Oh, yeah, sure. It is a mixture of wireless sensor network. It is actually an application of wireless sensor network in healthcare. Wireless, yeah. In this case also they. No, not through wire. They are connected to the personal digital assistant. That is they can be either connected to the smartphone of the person. No, it's not through wire. Like I have a sensor node for ECG, for motion, and for body temperature. All these will sense the different kind of information, and they will send it to my mobile device through a wireless technology. We'll cover those technologies later. This is done through wireless technology. Yes, sir. Yes, sir. Blood pressure. Yeah, sure. Yes, sir. Yes, sir. They are not connected to a PTPU. They send the data to a mobile node of the patient. That mobile node can be a smartphone. It can be any laptop. It can be a home computer. It sends the data to that system through wireless technologies. Yes, they have some Wi-Fi model. Yes. This is one of the recent research issues, like the sensor nodes are affecting the health. They, rather than measuring, they are affecting the health. This is one of the, with the wireless body area network sensors, they are different from the other sensors because they have to check that there should be no loss of heat. There should be no heat radiation because that will affect the patient. This is one of the research trends. This is the basic architecture of wireless body area networks, in which we can see a patient on which we have mounted many sensor nodes that sense the information, and they are sending the information to the personal server of the patient through Zigbee. Zigbee is a wireless technology. So this is a three-tier architecture, in which we can say the first tier consists of the W band, or the physical layer of the architecture, in which the sensor nodes are deployed, and then the tier 2 is the personal server, in which it's the patient level, or which we can say the data collection. The data is sensed and collected sent to the personal server, where it is aggregated. So the information is collected, and from the personal server, the information is sent to the doctor through the internet, through any of the GPRS or any 3G or 2G technologies. And the doctor there a database is created. The doctor can access the information, and the third tier is the communication part, in which the doctor accesses the information. But there are some prerequisites for the third tier of the architecture, because that as we are talking about the health data, it must be very secure. So the database on which the doctor is accessing the data, that must provide for the authentication levels, so that the only legitimate users are accessing the information. So it should provide all the security measures. So first tier consists of intelligent sensor nodes for sensing and sampling and processing the information. Second tier consists of the personal server of the patient. and third tier is a remote, consists of a remote server to which the data is to be sent. Next comes the positioning of wireless body area networks. In this figure, we see that there are two types of positioning. First is the intra-body communication, and second is the extra-body communication. In the intra-body communication, what happens is if we have deployed the sensor nodes on a human body, then all those four sensors, they send the data to a mobile node. So this makes an intra-body communication. So when from the mobile node the data is sent to the doctor through internet, that is referred to as extra body communication. So this is the only difference between these two communication, that intra body refers to the patient and extra body refers when the patient contacts the doctor. Next is the W-band components. We can say that they consist of two components, the sensor devices and wireless communication technologies. For a sensor device, as we have known till now, that they are capable of processing, gathering, monitoring information and communicating the data to the sync node. And they can be referred to as smart nodes because they are low power, they are not low power, low cost and multifunctional nodes. So there are three basic functionalities, that they are not too expensive, they can be easily purchased, they require low power, they don't require much power to work upon, and they are multifunctional nodes on which they perform many functions, like they sense the information, they can process the information, and they can send the information. And sensor nodes fall into the following categories. First is the physiological sensors. Physiological sensors are the biological sensors that measure the biological parameters like ECG, EMG, blood pressure, blood temperature. Recently, we have seen that there is a sensor device for checking the blood glucose level, in which we have to insert our finger, and they don't prick the finger without injecting any needle into our body. Without the blood, the sensor can sense the blood sugar level. So this is the latest trend of the sensor devices. And for EMG, for EEG, we have a chip in which we can implant the sensor on the brain of the person, and that sensor can actually sense what the person is thinking, and that can be converted to text or speech. So these are the physiological sensors. Then we have micro electromechanical systems, that is MEMS, in which there are sensor devices which can sense all the mechanical parameters like force, energy, or we can say they have pressure or acoustic sensors that sense the sound. All these parameters are sensed by MEMS. Then we have biokinetic sensors. Biokinetic sensors are a mixture of physiological and MEMS sensors. They sense the acceleration and rotation of the human body. The acceleration, for this is useful for athletes or sports persons. Suppose they are running, they have to check the speed or something. The biokinetic sensors are capable of doing this. And at the last, we have ambient sensors, which are capable of sensing the environmental parameters like humidity, temperature, heat, light, motion. All these can be sensed by ambient sensors. Next is the basic architecture of a sensor node. The basic architecture, it consists of the four nodes. The first is the sensor. It is a VLSI chip on which we have done some processing, and it is capable of sensing the parameters. But it is very application specific, as the sensor node depends which parameter we have to sense. So for a particular application, we have particular type of sensor devices. And next is A to D converter. It is analog to digital converter, which converts the sensed information into a digital signal and then transmits it. Next is the microcontroller. Microcontroller actually connects the sensor device to the battery source. We have a battery source. They connect it to the battery source. Then is the transceiver. Transceiver is the antenna which is used for receiving and sending the signals. But with these four basic structures in a sensor node, we have three more structures. That is the processor, the operating system, and the storage. The processor is a very light processor because they don't have to do much processing. And operating system, there are many kind of operating systems have been developed today, but the basic is Tiny operating system. It is named as Tiny OS. So Tiny OS, what it does is, it has a tiny operating system. So Tiny operating system is actually used for concurrent data flows. It is event-based operating system, in which when an event is triggered, the operating system starts working. The difference we are using in sensor devices, we don't use that stack-based operating system, because there some extra storage is required to have store a stack, all the and then there is some extra energy is wasted in context switching. So we use event-based operating system, and then we have small memory for the sensor devices to store for a little time they can store the things. Next comes the radio frequency technologies, which are used in W bands to transmit the data to the mobile node. So we have three technologies, that is Zigbee, Bluetooth, and ultra wideband. So Zigbee is an IEEE specification, and it is a high-level communication protocol which is used over short ranges, or which is used for two types of for applications with requirement. It is used for low data rate applications. So Zigbee actually applications require that the it should have secure network communication, and it should have low data rate. So it consume less energy. So W bands are this kind of application that they have they consume less energy. They must consume less energy and secure information transmission, because it's about health information, so it must be secured. And Zigbee provides security mechanisms because it uses symmetric key encryption using 128-bit symmetric key encryption, and it also has collision avoidance mechanism. And the transmission is 10 to 100 meters line of sight, but it can be increased by using star or mesh topology. So it is preferred over other technologies because it is simple to use, and it is less expensive than other technologies. So that is why it is used. Next is Bluetooth. Bluetooth is also an IEEE specification, and it is used for wireless communication over short ranges. So it works for the frequency band 2.4 to 2.485, and it creates a personal area network that is known as PicoNet, in which we have one is the master device, and it can connect to 7 slave devices, and it synchronizes according to the master clock. So when the device is synchronized to a master clock, so it can share the data. It has a high bandwidth and low latency. Then next comes the ultra wideband. Ultra wideband is also an IEEE specification, and it is used for short range low energy level communication. It is basically used inside a building for indoor communications. For example, if we use ultra wideband inside ambulance, it can tell us that which route to take which has less traffic. So this is useful in case of indoor communications. It is not much used in W bands because it increases the complexity. Because we have to use ultra wideband with GPS. So GPS increases the complexity of the devices which we are using. This is the comparison of these radio technologies, in which we can see that Zigbee is a frequency band, has ISM, and its data rate is 250K, and the multiple access method is CSMA. So it is collision. It has no. This is carrier sent multiple access method, in which there is no provision for collision detection or this, but that can be included into the Zigbee. Then coverage is 30 to 100 meter, and then network topology star or mesh. And then in Bluetooth, it uses multiple access method of FH and TDMA, in which there are time division multiple access method is used, in which we divide the channel into time slots, and each node is having a particular time slot in which it can send the data. And it uses network topology of star. Next is ultra wideband, in which we have multiple access method of OFDM, that is orthogonal frequency division multiplexing, in which what we do is we divide the frequency such that the orthogonal neighbors, the subcarrier, or we can say the nodes which are orthogonally neighbors, they send the data in a single channel. And it also uses the star topology. Next comes the MAC protocols, in which we are using the W bands. For wireless body area networks, we have MAC protocol. The basic MAC protocol occurs in the data link layer, that is above the physical layer and below the network layer in the OSI model. And for the MAC protocols, the basic functionality is the access regulation for shared transmission. That is, it has to decide as to which node has to use the channel at what time. So this is the basic functionality of the MAC layer. Like if there are 10 nodes in the channel, they have to decide according to what basis they have to decide that which node will choose the which channel and at what time. So what the other functionalities of MAC protocol includes that when it receives the data from the physical layer, it assembles the data into frames. It adds the header and trailer and for error detection and error correction purposes. And then when the data which it receives from the network layer, it disassembles it into frames. Yes, sir, because the data which is being sent is sent in the form of packets. For it works, body area networks, they work at all the layers. We have physical layer, network layer, transport layer, MAC protocol, all these things are working in these. Because without this, the communication is not possible, because the communication technologies are normal wireless technologies. Zigbee is used elsewhere also, so we can't change the protocol.
So as far as body area network is concerned, where we are communicating with the multiple types of sensors.
Yes, sir.
And then that gets processed with the external layer.
Yes, sir.
Transfer to my
Mobile node.
After
that
packet.
Yes, sir. Personal server. Yes, sir.
That may require routing.
That definitely requires routing and all. So before that also we require routing, because what happens is wireless body area network actually is formed of two types. Like if I have a 4 sensor nodes on my body, that 4 sensor nodes can form a network. And for example, we have a hospital in which there are 100 beds and the 100 patients, and we deploy a single sensor on all the 100 patients. That 100 nodes can also form a network. That case occurs, we have to cluster the nodes so that they can send the data to a single, they have to send data to a single mobile node. So these things occur in that cases when we create clusters from intra WBAN clusters. That is required. Individual, it may not be required, but in case we have, because in today what research is going on wireless body area network is according to this. Yes, sir. It depends upon, they are application specific. It depends upon the application where we are using the wireless body area network and how we have to use them. I have to reduce energy consumption. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Overhead. So, but these things are required for the communication process, because the overhead is not occurring in the case like I have to send data to my personal server. There will be no overhead. There will be no delay. That sensor nodes are sensing my data, and that device is used by me. How can there can be a delay? So the delay occurs after that, when the data is actually on the transmission channel. After that. So there are 3 types of MAC protocols. First is low power listening, second is scheduled contention, and third is TDMA. So in low power listening, what happens is the nodes have 2 type of modes, that is sleep mode and the wake mode, and they are on energy consumption mode in the sleep mode. They wake up from the sleep mode, and then they sense the channel. If the channel is free, they send the data. If it is not free, they again go to the sleep mode, and after random amount of time they again come to the wake mode and check. But this is least desirable in wireless body area network because it does not support aperiodic data. So as wireless body area networks, they have heterogeneous and aperiodic data, so this is not as useful as others are. Next is the scheduled contention, in which the contention means that there is no predefined schedule has been defined. There is no access as to which node will send the data first. Whenever a node has data to send, it sends the data. So there occurs the case of collision. Like there occurs the case of collision, packets are collided and they have to be retransmitted. And retransmission is very difficult in case of sensor devices, because sensor devices have low memory. They can't store the information. So if the packet is retransmitted after a lot of time, till then the sensor devices will erase their memory. So so it creates a problem. So then we have scheduled contention. In what we do, that is, we have a common schedule for a channel for one kind of nodes. For example, we divide the wireless body area networks into clusters, and one cluster will have one schedule, another cluster will have another schedule. And at one schedule, only nodes from one cluster can send the data. They have provision for choosing a node, which node will send in which cluster. So what happens in this case, the problem occurs when there are two neighbor nodes and they are in different clusters and they have to compete for channel. So what happens is they have to keep the schedules for both the clusters. So there then occurs the case of the collision. So there can be a collision, or there must be some, they are consuming energy in saving the schedule of both the clusters. Next is the time division multiple access, in which this is the best protocol for W bands, because as we divide the channel into times, then each node is slotted a particular time slot according to the data volume. If the data requirement is more for a particular node, we can increase the time slot. So this is very useful for the wireless body area networks. Next come the W-band characteristics. In W-band characteristics, the first is the architecture, in which we check for the number of nodes in a W-band, or we check for how the topology of the network is formed. Next comes the latency. In latency means the delay that occurs in sending the data to the sync node. In this case, this is also a latest research. Which we can say that the wireless body area network is divided into two types: the urgent and the non-urgent data. So what happens is, for urgent data, we can say that requires quick feedback from the doctor. So that data must not be delayed. It is when it receives, it is sent as soon as possible. But in case of non-urgent data, we can add delay to that data, because it does not require quick feedback from the doctor. So in case of next is the density. Density occurs when there is a case of data redundancy. So as we don't have redundant nodes in wireless body area network, there is no issue of data redundancy, but there comes the issue of information loss. Information will be lost, and information will be lost, and we cannot retransmit the packet easily. Next is the data rate. Data rate can be very stable or astable, depending on the application or depending on the data which it is coming. So these are the basic characteristics of the wireless body area networks. Next come the advantages for wireless body area networks. The first advantage is the promotion of healthy lifestyle. How wireless body area networks propose this thing? Because with the help of wireless body area networks, what actually is that we have to be at our own place. The patient has to be at his own place, and he is not required for the doctor. So doctor can access the information at its own clinic, and patient does not need to move to the doctor. And the basic thing is that every time you're being monitored. The benefits of unobtrusive monitoring, that means that it is no obstruction is occurring in being monitored. So as you are continuously monitored, so the patient can go for checkups or something, the doctor can prescribe something. So this promotes healthy lifestyle. Next is the personal medical records and research databases. We create a database at the server end, from where it is accessible to both the patient and the doctor. So what happens is, from those databases, we can search for long-term trends which are occurring with the help of data mining. We can check for the trend analysis. We can check for the abnormalities that occur in the database. So these all are actually proactive versions of the W bands that can help the patient to be the disease can be detected, diagnosed beforehand. Every time it is not possible that you are ill and you can go to the doctor. So this is possible in case that you can beforehand you can know what things you are facing. Next is prompt alerting of a caregiver to intervene in case of an emergency. For example, if there occurs a case of emergency, the doctor can alert the family members. The patient is moving. In case the patient is moving, we have to check for the patient distance, at what speed it is moving, at what where the patient is moving. All this information can be sent to the patient's caretaker and through the doctor. So they can be alarmed that patient has to be taken to the hospital, or any prescription is to be given to him. Reduction of errors. We have seen many cases in normal life that the doctors, they cannot provide the correct diagnosis. There are some kind of errors in case of manual prescriptions, or in case of manual diagnosis. What happens is, the latest technique which is used is, like, we have a person who is hospitalized, and the sensor devices, they are sensing the data, and they are connected to a computer system. While they are connected to a computer system, from the computers, with the help of artificial intelligence, that computer gives the information as to which, that computer diagnoses the patient as to which disease can happen or what cannot happen. They just sideline the doctor. So there can be no provision of manual errors. This is one of the latest research trends in wireless body area network, mixing the W bands and artificial intelligence. Next is reduction of hospital stays and visits to doctor. That means that person is present at its own natural environment, at its home, where it is being observed. He does not need to move to the doctor. Every time for a regular checkup, we need not move to the doctor. The data is sent to the doctor. The doctor can observe the data and can prescribe something. This is very useful for patients for whom it is very difficult to move to the doctor. Next is extending independent living for senior citizens and improve patient comfort. So in this case, we can say that the people who face difficulty to move to a different place, they have a lot of benefits with the help of wireless body area networks. The sensor devices are used, which can check they can detect the disease, they can diagnose the disease, and they can live happily in their own environment. They need not move to the hospital for a regular checkup. The basic problem with our conventional healthcare system is that there are long queues in the hospitals. People have to wait to visit to a doctor. This is the case with the private sector, and in public sector we see that the private hospitals or private doctors, they are not easily affordable. But in case of W band, this is easily affordable, and this is every time this system is giving us the approach to be monitored. So this is very useful in case of, maybe it is not every person cannot afford W band, or cannot be used by everyone, but more people can use it. Most of the people can use it, even in our country, we say they can be used by our country, and so this can promote a healthy healthcare. These are the various wireless body area applications in which we see that we can diagnose the various diseases. We can have personal health care, we have entertainment, we have defense. This is very useful in defense services, as the soldiers can be monitored through a sensor device, and they can give the information. The information can be sent to their contingent, to whom they belong, and then from there they can guess what happens to a particular. For example, we have seen that in Siachen, many soldiers, they die of lunch or something. Their health issues are occurring in Siachen Glacier, where the soldiers, they have been deployed. So if we use W bands there, their health related information can be continuously monitored, and it is very useful for such cases. Where? Nursing is not feasible. It's not feasible if we can provide. So sensors are actually made for the places where there is absence of human mind. So where human mind cannot be present, we can deploy a sensor node, and then the sensed information can be sent back to the human. In sports, these are very useful because the sports person or athletes, they need to continuously measure their muscular activity so that there's no muscle pull or something, or what drugs they should take for better performance. So these are very useful in sports also. And there are basic applications of wireless body area networks which are not medical related. They are non-medical applications also. Like we can go for the gesture detection. Like from the gesture detection, we can have an emotion detection. At this, the person is having this kind of gesture, and he is referring to what emotion. So this is very useful. This is in these things are all used with the help of artificial intelligence. This is supervised learning, in which we have to train the sensor devices. Like these kind of emotions are occurring, then what happens? This is classified learning. We can't say six senses of human beings, not of sensor devices, but yes, we can create a link between the two things. Like if I am posing like this, what emotion I'll be having at that time? These can be sensed by the sensor devices. These are the another application which I was saying are medical and non-medical applications. For example, for the wearable wireless body area networks, there can be wearable health monitoring. We can have soldier fatigue, aiding professional sport trainings, then sleeping staging. Some people this is useful for the people who are in coma, like their brain is working or their other senses are working. We can sense what they are actually thinking. Then we have implant wireless body area networks, for which the cardiovascular diseases, they can be checked. Implanting means to embed inside the human body, and the life for the implant sensor devices 5 years or round about 5 years. For cancer, the very popular private hospitals, they are using these kind of things for cancer detection. Then we have remote control of medical devices, that is ambient listed living, patient monitoring, telemedicines. Telemedicine is we have seen everywhere, like which kind of medication is provided to a particular patient, and what diseases it follows, and what are the side effects. All these things can be measured from these things. Then we have non-medical, that is real-time streaming, entertainment application, emergency, where we can contact the patient in case of emergency. We can contact the family, doctor can give the prescription. So the basic idea is that we can integrate the information technology and healthcare. So the basic idea of this is W bands is that with the help of sensor devices, we can sense what the human body is doing. These are the basic major research issues in W bands. First is the MAC protocols. The major research issues going in the MAC protocol is the low power and secure MAC protocol. What happens is the radio frequency technologies which we're using for transmission or for communication, they are consuming most of the energy of sensor devices. So what we need is for the MAC protocol which we are using, they must be power efficient so that not much of the energy is consumed. There have been many techniques have been proposed for these things, like they use low data rate applications. They have created that such the frame size is small. They have reduced the frequency band, or they are changing frequently changing the frequencies so that the less energy is consumed of the sensor devices, because the only thing we can optimize in sensor devices is their energy usage. If they use less energy, then only we can enhance the network lifetime. So there are many, but in MAC protocol, then there occurs they use different frequency band, but then there occurs the problem of collision detection, because some frequency band they don't have, some protocols they don't define the collision detection, and if collision occurs, then there's again the issue of retransmission of packet, which is very difficult in case of W bands. So there is one issue in the case, some research is being done in case of periodic data, but W bands more or less they have aperiodic data. So some research is done in this case, like if all the defined protocols. They are on periodic data. What happens if they are tested on aperiodic data? This is the major research trend in case of MAC protocols. So the another comes with the battery aware, that is TDMA. It has packet drop is high, but it improves the network lifetime. What happens is uh, another case is MAC security. Thus, these protocols should also provide the security to the to the application, because securing the health data is of prime priority. So what happens is they should provide confidentiality, integrity, privacy, authentication, key establishment. All these things should be provided by these MAC protocols. They must be having high in case like we are creating a database in which we are storing the health information. There are 100 patients connected to a single hospital. They have their own private server on which the 100 patients are sending the information. So that server must be secured. If the doctors are having access, there must be some authentication protocol which is being used, so that the data is accessed by legitimate users. Because in regarding our government schemes also, we have a HIPAA protocol, which is for the prevention of the health act or health information, something it is. So all these things are required in case of W bands also, that we security research is going on. A lot of research is going on MAC security. So that the latest research trend is, if we have cipher, what happens if we have ciphertext is of same length of the plain text, because the data is not large enough for in case of W bands, the data is small. So what happens if we encrypt the data and the ciphertext is of same length of the plain text? We are using many techniques, that is the cyclic redundancy check or the AES scheme, and then we symmetry key, asymmetry key. All these are being used in case of MAC, providing security to MAC protocols which are used in W bands. But the thing is still this, that we don't have a perfect MAC protocol which can be low power and at the same time it will be highly secure. So we don't have this, but there are many schemes which are very good, but still we don't have the perfect protocol. And in case of applications, what application where these are used? Sorry, where the W bands are being used. So what happens is many researchers, what they are doing is they are creating a W band prototype. They are creating a scenario in which we have number of patients where sensor nodes are deployed. They're sensing the data and then sending it to the mobile node. From mobile node, we are sending to a particular server. But still there occurs many problems. So they have integrated cloud computing. Cloud computing provides the basic features, like we have a cloud with extensive resources. There's no lack of processing power or memory or storage. So we should integrate these things with cloud computing. Like one of the researchers, they proposed a health integrated management system, HIMS, in which what they did was they started sharing and accessing the medical information of many. They created a cloud in which the number of hospitals stored their server on the cloud, their data on the cloud. So means we can say that for many hospitals there was single server, single cloud on which their data is stored, and they from that cloud offers the services to their patients and to the doctors, from where they can access the data. And this was a hybrid cloud in which many hospitals they created a hybrid cloud and they formed it. But this is still again there occurs the security issues. So there are a lot of researches going on. Another researcher, they proposed a health monitoring system in which they created it for telemedicines. Utility computing is used, like they are connected to the medical equipment. Sensor devices are connected, rather than being connected to the patients, they are connected to the medical equipment. And medical equipment sense what? Because then we can detect the equipment is faulty or not. We can also check patients are connected to the sensor devices are connected to the patients, and then their sensors are also connected to the equipments which are being used. Again, the problem is with these e-health. These are referred to as e-healthcare systems. They are robust. They are robust because the data is stored on the cloud. They are portable because patient can move from one place to another. Next comes is the certification, in which we have to check for the quality of service for the case of wireless body area networks. In case of these, we provide healthcare system. These systems are referred to as e-healthcare systems, and they are reliable because data is highly secured. There are issues, but they are still very highly secured. So patients are sending their information to the common server, which is accessible to the doctor. So it must be reliable. Then we have the portable systems that they can be moved to any location. We have a robust that where we are storing the data. It must be fault tolerant. If anything goes wrong, the data should not be lost. And from the database, there is complete profile of a single patient. The patient can check their patient profile or their anything. Doctor can access on the give their prescription on the basis of the database. Then we have in the case of routing protocols, there are two types of routing protocols which we use. First is the temperature based. What happens is a lot of research is going on this field. In temperature based routing protocols, what happens is like when we deploy the sensor nodes on the human body, they affect the tissues of the human body. They absorb the heat or they generate a lot of heat while processing, like they affect the human body. So a lot of research is going on as to what kind of sensors must be designed so that they can be they cannot affect the human tissues. In this case, the biggest issue is like the temperature of a particular sensor device is increasing. For example, we have deployed 4 sensor nodes on a human body, and the temperature of one of the node is increasing. We refer to it as a hotspot. What happened now? We want that sensor to shut off. We don't want that sensor to work because it is affecting the human. Instead of measuring any parameter, it is affecting the human being. So what happens is the tissue starts breaking. Before that happens, what we do is we call that sensor node as a hotspot. We call that sensor node as a hotspot. So the basic issue occurs like as to we have to stop working with this sensor node. So what happens is all the packets of that sensor node, they are rerouted to a different sensor node or they are sent to somewhere else. So the problem here occurs as to which node is to be chosen next. If a sensor node has stopped working, it is a hotspot, it is temperature is rising, but which node, the packet should be rerouted to which node, which sensor node. So this is the issue, which node should be chosen. So the basic thing is that we should choose a node which is the next hop node, but with lowest temperature. Because if we send so many packets to a single node, that will increase the temperature, then it will be created as a hotspot. So in this case, the number of hop counts increases. That packets have to move to a number of places before they can be sent to a sync node. So this is the basic issue with the temperature-based routing protocols. Like which node should be chosen as the next hop for if a sensor node is declared as a hotspot. Next is the cluster-based. Routing protocol, in which what happens is like we have so many sensor nodes on a patient of a single patient on a single human body. We deploy so many sensor nodes and we create one cluster. We have another patient, we are deploying so many sensor nodes on that patient and we make it another cluster. So we have a leech. Leech is a clustering algorithm. Leech is a low energy adaptive clustering algorithm. So what happens in this case is we create clusters and we choose cluster heads, and the cluster heads, they keep on rotating. But in this case of WMANs, they can't be rotated because they are on a single patient, so it cannot be rotated. So by choosing, but a single node can be chosen as a different nodes can be chosen from single patient. Different node can be chosen as a cluster head. The node with the lowest temperature or the node with the maximum energy, which is left with the maximum energy, can be chosen as a cluster head, and they start moving from different rounds. So energy, in this case, the energy efficiency is improved. Like when we are sending the packets to different sensor nodes, this improves the energy efficiency. We'll demonstrate the leech protocol. But here occurs the conflicting interaction between nodes as to which node is to be treated. If there are two nodes which are capable of becoming a cluster head, which node will be selected for cluster head? These kind of issues occur in these protocols. Then is the physical layer. Physical layer, there's a lot of research going on how to design a sensor node. So that they have maximum battery lifetime, they have enough storage, but they should not heat the human body, or they should not the other protocols or other structures which we are using in a sensor device, they must not consume the maximum energy of the sensor device. For example, we are using stack based operating system, it will consume maximum energy in switching is consumed. So the sensor node will be cannot sense for a long. It will be declared as a dead node very early, because a lot of the energy will be consumed in that case, and less energy will be used, and it will have less energy, and then it cannot sense for a long period. So these kind of like which transceiver, this is little electronics based as what devices or what structures are to be used while designing a sensor node. Next comes the issue with security of the W bands. Security, we also provide the security and privacy. There are issues, but they are the same cases as we have already learned, that we have to secure the patient data, or we have to secure it but at what level we can provide security? The sensor nodes should be self-capable of providing security, or the mobile node to which we are sending the data, it should be capable of providing security, or finally at the remote server where we are sending the data, it should be capable of providing security. So but if the sensor nodes are themselves providing security, it will consume energy. So there are many issues like this, but the best case is if the energy is the security is provided at the mobile node and at the remote server. But still there are issues if before sending the data to the mobile node, if data gets corrupted, there are issues, but this happens very less. Many researchers are working in this phase, but there's no particular scheme which can be which provides security at all the levels. There is one issue in W band, that is of data aggregation, that occurs at the middle tier, that is at the mobile node. So what happens when we send the data to from sensor node, the data is sent to a mobile node. So what happens is that mobile node should aggregate the data, it should club the data, because we are sending more number of packets to the transmission, it will ultimately cause congestion on the transmission channel, so it will lead to so many problems. So what happens, there are recent researches on how we can aggregate the data. Like while aggregation, there should be no loss of data, and there should be not enough number of packets while sending the data, so that the transmission channel, resources of the communication channel are reserved, they are not wasted. Then occurs the issue of localization, that position measurement of the sensor, that defines where the sensor node should be deployed to sense this maximum correct information. This is one of the areas where the research is going in case of wireless body area networks. Next comes if we integrate cloud computing and wireless body area networks. So what happened? This is the diagram of this paper mentioned here. The researchers have done this here. Like they have created their own network in which they have a number of patients on which they are monitoring. They have deployed number of sensor nodes on many patients, and then they have created their own network using routers and gateways, switches. This is the CHMS software. So what this is referred to as a local W band, where there are many patients. There are 4 patients. They have taken 4 patients in a diagram, and then they refer to as this is a local W band. And they send the data to a single router, and then from there moves to a global cloud. The data is moving to a global cloud from where it is accessible to the doctor. So they are not that sending to a remote. That remote server we can say is cloud. So where they are sending the data. So this is very useful because hospitals also, they don't need to have to create their own server. They can move to cloud. So this will provide the basic functionalities which the cloud computing is providing. So a lot of research is going in this field. Why shall we integrate cloud computing and WBANs? Because WBAN basic issue is that sensor devices, they have low resources. They don't have enough processing power. They don't have enough memory. So what if we send the data directly to a cloud? Without they have sidelined the mobile node. They have directly sent the data to a cloud, and this is the global WBAN in which the data is sent to a cloud, and from where the doctor can access it and can give the feedback. Next comes the practical demonstration. First, we'll see the things in MATLAB. We'll take a break of 5 minutes and then we'll start with the practical demonstration. पर्सनल हेल्थ केयर के लिए So now we are starting with the practical demonstration. First, I'll show you how to create a the wireless body area network or wireless network in MATLAB. So in this case, this is the figure in which we have 12 sensor nodes. These red nodes are the sensor nodes, and then this is the green node is the server node from where the sensor nodes are detecting the data and they are sending it to the server node. So this is done by using simple MATLAB methods. Like we can have we define the region, like this is a particular region in which we want our sensor nodes, and then the sensor nodes can send the data to a server. This is the sync node on which we are sending the data, and then this is this is the data flow is also shown with the help with the help of blue lines. The data flow is shown, like we are sending the data. So now in this program we can integrate any kind of program, like what kind of data we want to sense. If we want to sense ECG data, we can have embed the ECG program, ECG code in this program, and they will sense the sensor nodes will sense the ECG data, and then they can send the information according to what ECG they have shown. Like this is the ECG data. This is the ECG data. So this can be this program which I have run, and this can be embedded in that program, and then it can be used to sense this kind of the sensor nodes will sense this kind. We can integrate the sensor nodes and the data which we have to sense. Then they will sense this kind of data, and the results will be shown. But we cannot show the data flow, like what data they are sensing and what they are sending. We can just integrate in this simulator. We can just integrate that what they are sensing and how they are sending the data to the sync node. But we cannot show that they are using that graph. That signal cannot be shown. And I have used as like we have defined a manual definition. We have given manually defined the sensor node as to by giving the XY coordinates. We can do that randomly also, like where we can set that. This was my program, which I'll show you the GUI. It is not working as show. So this is the GUI in which the here the upper graph will show you the sensor nodes and this network topology, how the network is created, where the sensor nodes are being at what coordinates the sensor nodes are deployed, and where is the sync node, and where is the cloud server from where the sync node is sending the data. And this will give the lower graph will give you the ECG signal in which we have compressed the signal, and then it will show the signal here. And on the monitoring panel we can see that which patient, how many patients are there in the network, and which patient is having what kind of ECG, means it's either normal, critical or super critical. So which data needs to be sent to the cloud as soon as possible. So we can define from this. If we start the simulation, so we have seen, we get to know about the topology of the network. So there are total 25 sensor nodes which are sending the data first to the sync node, and from the sync node they are sending the data to the cloud. We can see that the sensor nodes, how they are sending the data, how they communicate with each other. So this is the value that the for the I node 17 the answer that they are sending data to this node. So this is the 25 is the value for the sync node. So they are sending data to the sync node. This is the Leech protocol about which we have studied. Leech is a clustering protocol in which it reduces the energy consumption. So we'll see how it works in case of wireless body area networks. So these graphs are showing the number of packets sent to the base station and versus round. How many? How at what round what is the number of packets? And this is the number of dead nodes in the network. How many dead nodes have occurred? And this is the sum of the energy. With the increasing number of nodes, sum of energy consumption is decreasing as the clusters are. But this is the case because MATLAB is not basically used for wireless body area networks. So we cannot actually see how the clusters are rotating in case of Leech, how we are moving. We'll see that in a video for a different simulator. So let it finish its working. This will There are no dead nodes because this is working. The time taken is very less, so that is why the number of dead nodes are zero. Because after sensor node, it is not like this. When we start the network, it will start having dead nodes. After a long time, they will start showing you dead nodes. So this will go on till we have defined the number of nodes, number of rounds. Now it is having number of dead nodes. Number of dead nodes are rising because the nodes which earlier were declared as cluster head, they might have been declared as now dead node because no energy is left in them. Because the work of a cluster head is very powerful. The sensor node which is to be declared as a cluster head must be very powerful. It must have maximum residual energy so that it has to combine the data from all the sensor nodes in the cluster along with its own data. So it must have huge amount of energy. So with the increasing number of rounds, we can say that the number of dead nodes are increasing. Shall I close it? This will because go for long. This is the network. So this was in MATLAB, but MATLAB does not clearly show the working of sensor network. So the simulators which are either we can work on network simulator or we have NetSim, but it is not freeware. So I'll be showing you a video in which we can understand how that simulator works. The video. ये NetSim वाली ऊपर ऊपर
एक्सक्यूज मी सर, सब माइक म्यूट है. एक्सक्यूज मी मैम, ऑडिबल नहीं है आपकी आवाज़.
Hello. They're from CB Raman College of Engineering, Bhubaneswar.
Yes, sir.
So voice is not audible to us.
Video.
Us.
No longer presenting the
मैम आपकी आवाज़ ऑडिबल नहीं है। हेलो, NI RRR चंडीगढ़। मैम आपकी आवाज़ ऑडिबल नहीं है, आपका माइक म्यूट है।
Sir, actually, we're displaying a video. Sorry. So as we have seen in the video, we can the better placement of wireless sensor networks rather than in MATLAB. As we have seen, this is the topology of the network which we can show in the MATLAB. So this is it with the session. Thank you. Any questions? Any questions?
Remote center, any query? Remote centers? Any other centers?
No queries.
Okay. Session is end. Tomorrow meet is 9:15. Okay.
Can you show the last slide again?